The signal arrived at precisely 3:17 UTC on November the 12th, 2025. Detected simultaneously by multiple radio arrays and space-based observatories, its arrival was subtle yet unmistakable, a narrow-band pulse emerging from the general coordinates of 3I Atlas. At first it registered as a faint blip, barely above cosmic background noise, but its consistency was undeniable. Within minutes, confirmation alerts cascaded across international monitoring networks. This was not an artifact of terrestrial interference. The signal's initial properties were immediately puzzling. Its frequency, centered at 4.19 GHz, did not correspond to any known natural emissions from solar or interstellar sources in that region. Amplitude variations appeared patterned, repeating in intervals of approximately 12.3 seconds, suggesting a mechanism of modulation rather than random cosmic turbulence. Early automated analyses flagged it as non-natural, a classification reserved for phenomena that defy standard astrophysical models. Observers noted that the signal's timing coincided with 3 Atlas's current orbital position, offering the first tangible link between the object and the anomalous transmission. The data showed no Doppler shifts consistent with a conventional spacecraft trajectory. Instead, the signal seemed to maintain a near-stationary alignment relative to Earth, as if calibrated to communicate across the vast distance with precise consistency. What makes this moment extraordinary is the convergence of multiple factors. 3I Atlas has long been under surveillance, a catalogue of anomalies documented over years. Observatories recorded unexplained electromagnetic emissions, unusual thermal signatures, and irregular orbital dynamics. But none had ever produced a signal with this structure, frequency, and intentional rhythm. Until now, the anomalies were suggestive. This pulse is definitive. Within hours, global monitoring centres began the first round of cross-validation. Arrays in Europe, North America, and East Asia independently confirmed the pulse. Space-based instruments reported a corresponding energy spike, corroborating the Earth-based readings. Redundant systems designed to filter out interference failed to dismiss it. Analysts began drafting initial reports with extreme caution. There is no precedent in modern observational history for a pulse of this type emerging from a near-Earth interstellar object with such specificity. The implications are immediate and profound. The signal is structured, deliberate, and detectable across multiple observatories, yet it carries no immediately intelligible content. It is a message in form, not in language, an encoded presence. Scientists are beginning to ask questions previously confined to speculation. Why now? And why from 3I Atlas? What does this reveal about its capabilities or composition? Is this a natural process we have yet to understand, or evidence of an intelligence operating beyond terrestrial assumptions? As the first waves of data were logged, researchers began to model the signal's behavior. Its modulation pattern suggests a sequence that could represent numerical or binary information. Though the full method of encoding remains unclear, noise analysis rules out random cosmic interference. The energy profile indicates a source capable of producing coherent signals over millions of kilometers. This is not incidental radiation. It is deliberate, detectable, and repeatable. But even as these conclusions form, one question remains unanswered. What does it mean? The raw data offers certainty in detection, but uncertainty in interpretation. Every subsequent chapter of analysis will attempt to bridge this gap, to move from observation to understanding. And yet, the signal itself continues, pulsing in quiet repetition, a measured heartbeat from 3 Atlas, asking Earth to listen, demanding scrutiny, and leaving a trace of profound cosmic questions in its wake. This is where the story begins. The signal is real, its source is identified, and the implications ripple across the scientific community. But how this pulse originated, and what it truly conveys, will take careful, deliberate investigation to unravel. We turn now to the first detailed examination, the characteristics of the signal itself, measured, analysed, and compared against known cosmic phenomena. The signal's characteristics are the first layer in understanding the unprecedented event. At 4.19 GHz, it sits within a portion of the microwave spectrum that is relatively quiet in natural cosmic emissions, a region often favoured in searches for artificial signals. Its narrowband nature immediately sets it apart. natural astrophysical sources, pulsars, quasars, and solar flares emit across broad frequencies, their spectra diffuse, fluctuating, and largely stochastic. This pulse, however, is sharply defined, a tight spike against the background, maintaining its frequency with remarkable stability over successive intervals. Amplitude analysis reveals subtle, deliberate modulation. The pulse strength rises and falls in a consistent cycle of 12.3 seconds. On initial inspection, these variations might appear random, but Fourier transforms of the waveform expose a repeating harmonic structure, suggesting a layered encoding mechanism. It is not a simple on-off pattern. Within the signal, finer subpulses, some lasting fractions of a second, carry energy distributions that defy immediate categorization. Each of these microvariations contributes to a complex rhythm that cannot be attributed to conventional astrophysical processes. Polarization studies add another dimension. The signal exhibits a degree of linear polarization that aligns closely with 3I Atlas's rotational plane. This alignment is precise, implying either an extraordinarily coincidental natural effect or an intentional directional orientation. If deliberate, this would suggest not just transmission, but calibration, tuning the signal to ensure reception on Earth with minimal degradation across interstellar distance. Even minor misalignments would scatter the energy, reducing detectability. The persistence and clarity of the signal indicate careful design. Spatial origin tracking confirms a fixed point relative to Earth, discounting a transient cosmic event. Unlike pulsars, which rotate and beam intermittently across predictable paths, or fast radio bursts, which appear once and vanish, this signal maintains a consistent trajectory tied to 3I Atlas. Its source appears to hover in a stable frame, as if observing, awaiting, or attempting communication. Doppler analysis reinforces this, showing minimal frequency shift despite Atlas's complex orbital dynamics. Spectral content examination reveals additional anomalies. Within the primary pulse, there exist secondary frequency components spaced at intervals inconsistent with known cosmic noise patterns. These sidebands carry measurable energy, but show no dispersion expected from natural sources traversing interstellar plasma. The structure hints at layering, a nested set of signals within the signal, a signature potentially encoding information at multiple scales. Each layer could be interpreted independently or as part of a composite message. Contextual comparisons amplify the unusual nature of the pulse. Historical observations of 3I Atlas reveal intermittent radio emissions, thermal spikes, and slight magnetic fluctuations, but none exhibit the coherence seen now. Previous emissions were considered anomalies, possibly linked to orbital dynamics or material interactions. This signal, in contrast, is precise, consistent, and exhibits complexity that cannot easily be reduced to stochastic astrophysical phenomena. Temporal analysis is equally compelling. The 12.3 second modulation interval does not correlate with Atlas's rotation, orbital period, or any known natural cycles. The timing is precise, and over successive observations, minor variations suggest deliberate adjustment or adaptive modulation. The possibility arises that the signal is not static but evolving, an active transmission rather than a passive phenomenon. Noise patterns surrounding the signal further distinguish it. Background analysis confirms the absence of interfering terrestrial sources, satellite chatter, or reflections from other cosmic bodies. Every redundancy check, every filtering algorithm reinforces the conclusion: the pulse is genuine, coherent, and distinct. Its consistency across multiple independent observatories worldwide confirms that this is not an artifact or error. Finally, the energy required to produce such a signal at this distance is non-trivial. The source must either harness substantial electromagnetic power or possess mechanisms far beyond current human engineering for targeted interstellar communication. This raises immediate questions about 3I Atlas's composition, internal structure, and potential mechanisms for signal generation. Whether it is natural, artificial, or a combination of both remains the central puzzle. Taken together, these characteristics establish the pulse as an extraordinary anomaly. It is structured, directional, repeatable, and energetically significant. Every measurable property, frequency, amplitude, polarization, modulation, and energy profile, points away from conventional astrophysical explanations and toward an intentional source. Yet interpretation remains elusive. observers are left with a signal that demands attention, invites speculation, but refuses simple answers. The next layer of the investigation turns toward how the signal was detected, the instruments involved, and the methodologies that ensured its reliability. Understanding the detection framework is critical, because only through rigorous observation can the scientific community begin to parse intent from artifact. The detection of the signal was as methodical as it was extraordinary. Multiple observatories across the globe, each equipped with specialized radio and space-based instrumentation, registered the pulse independently. In Europe, the LOFAR array in the Netherlands captured the initial ground-based signature, its high-resolution interferometry revealing subtle structural components within the waveform. Simultaneously, the Greenbank telescope in West Virginia recorded the same pulse, with a slightly different perspective, allowing scientists to triangulate its precise origin with unprecedented accuracy. East Asian facilities, including the FAST radio telescope in China, provided additional cross-validation. Ruling out local interference or equipment anomalies, redundancy was key. Each site employed independent signal processing algorithms, ranging from traditional Fourier transforms to advanced machine learning models trained to differentiate natural cosmic emissions from potential artificial transmissions. Every system flagged the signal as non-random, yet each approach revealed slightly different nuances. These minor discrepancies were not errors but complementary layers of observation, highlighting aspects of the pulse invisible to other methods. The combined datasets allowed a more granular reconstruction of the signal's energy profile, revealing both macroscopic patterns and fine-grained microstructures. Space-based assets added a third dimension. The orbiting deep space array, positioned beyond Earth's ionosphere, confirmed the pulse without atmospheric distortion. Its data demonstrated that the signal's coherence persisted across the interstellar medium, showing no expected dispersion from charged particle interactions. This alone suggests a source capable of compensating for, or entirely avoiding, natural interference, a trait rarely observed in cosmic phenomena. Instrument calibration and error checking were immediate priorities. Every participating facility ran exhaustive diagnostics. Sensors were recalibrated, antennas realigned, and signal paths verified. Sophisticated filtering algorithms were applied to remove potential interference from satellites, solar activity, or terrestrial sources. Each step reinforced the legitimacy of the pulse. By the time initial reports circulated among international scientific committees, there was little doubt. The signal was real, persistent, and extraordinary. Timestamping played a crucial role. Coordinated observations synchronized with atomic clocks allowed analysts to pinpoint the pulse's arrival within microseconds. This precision revealed minor variations in the pulse's phase between observatories, differences consistent with a single, coherent source rather than multiple unrelated phenomena. It also enabled the creation of a three-dimensional model, effectively mapping the pulse as it travelled from 3i Atlas to Earth, showing a straight-line propagation across the intervening distance with no detectable deviation. Data security and verification protocols were immediately enacted. Preliminary findings were encrypted, transmitted to global partners, and mirrored across multiple scientific institutions to prevent contamination or premature speculation. The rigor applied was not typical for ordinary detections. The potential implications of an artificial or otherwise intelligent source demanded extraordinary scrutiny. Observational analysis also incorporated cross-spectrum comparisons. Optical and infrared monitoring of 3i Atlas showed no simultaneous anomalies, confirming that the pulse was specific to the microwave spectrum. High-energy instruments recorded no correlated gamma or X-ray bursts, further reinforcing the idea that this was not a natural astrophysical eruption, but an isolated, controlled emission. The methodologies used to detect and confirm the pulse reflect the intersection of advanced technology and meticulous procedural discipline. Each layer of observation, from terrestrial interferometry to space-based verification, builds an unbroken chain of evidence. It is this chain that provides the foundation for scientific interpretation. Without it, hypotheses would remain speculative. With it, every model, every potential scenario can be measured against concrete, reproducible data. The reliability of detection also opens a window into the signal's broader significance. Its repeatability and clarity across multiple independent platforms suggest intentionality. If natural processes could not reproduce this pattern, the evidence points to a mechanism, whether natural, artificial, or hybrid, that is precise and controlled. The detection framework is not just a technical achievement, it is the lens through which the anomaly becomes intelligible. Understanding the instruments and methods sets the stage for the next step: initial analysis of the signal itself, where astrophysicists begin separating what can be explained by known science from what defies it. Only by coupling meticulous detection with careful interpretation can the full nature of the 3i Atlas pulse begin to emerge. Initial analysis of the pulse immediately highlighted the tension between established astrophysics and what the data appeared to reveal. Once the signal's detection was confirmed, teams around the world began running simulations and cross-comparisons, attempting to reconcile it with known phenomena. The first challenge was classification. Was this a natural event, perhaps an unusual magnetohydrodynamic process, or an artificial emission intentionally directed at Earth? Natural astrophysical explanations were considered in depth. Pulsars and magnetars produce highly regular emissions, but their frequencies, spectra, and energy distributions differ fundamentally from what was observed fast radio bursts, which had long mystified scientists, were also analysed as a possible analogue. Yet far bursts are typically brief, often singular, and exhibit frequency dispersion across the interstellar medium. The 3i Atlas pulse, by contrast, was both sustained and narrowly confined to 4.19 GHz, with internal modulation suggesting deliberate structuring rather than random turbulence. Astrophysical modelling was exhaustive. Researchers considered exotic scenarios, interactions between charged particles and 3i Atlas's magnetic field, energy emissions from hypothetical internal processes, or reflective resonance phenomena. Each model, however, failed to replicate the combination of stability, modulation, polarization, and directional alignment simultaneously. While some explanations could account for one characteristic, none could account for the full dataset without invoking highly improbable conditions. Attention then shifted to the possibility of an artificial source. While this step is traditionally approached with caution, the pulse's characteristics, repetition, structure, and coherence warranted serious consideration. Within this framework, scientists analysed the modulation patterns, comparing them to binary encoding schemes, prime number sequences, and other mathematically derived signals. Early analysis hinted at regularities that could serve as a carrier for information, though the decoding remains incomplete. There is no guarantee that human interpretation aligns with the signal's intended structure, or that it even contains content in a linguistic sense. Signal entropy was measured to determine complexity. The results were striking. The internal structure of the pulse exhibits low randomness relative to natural emissions, yet not so low as to appear trivial or mechanical. This balance suggests a sophisticated form of information delivery, optimized for detectability across vast distances. The modulation cycles, subpulse energy distributions, and phase variations all contribute to a layered design. Such characteristics are rarely seen outside engineered systems. Contextual comparison with prior 3i Atlas observations reinforces the anomaly's significance. Past emissions, while anomalous, lacked the coherence and directionality of the current pulse. Thermal data, electromagnetic mapping, and orbital tracking had suggested unusual activity, but never produced a signal detectable at Earth with this clarity. This marks the first unambiguous instance where 3i Atlas appears to communicate in a form that can be reliably monitored and studied. Even as initial analysis progressed, the pace of scientific debate accelerated. Working groups formed in real time, analysing the same datasets under different theoretical frameworks. Some proposed hybrid explanations, natural processes amplified or channeled by unknown physical mechanisms, potentially producing the appearance of artificial structuring. Others cautioned against premature conclusions, emphasizing the limits of current human understanding of interstellar electromagnetics. Every angle was scrutinized, every variable tested, yet none fully accounted for the observed complexity. The implications of this stage of analysis are profound. The pulse exists as a measurable phenomenon, structured and deliberate, yet its underlying cause remains unconfirmed. Researchers are left with a duality: concrete evidence that defies conventional explanations, and an interpretive vacuum where hypotheses, astrophysical, artificial or hybrid, compete for plausibility. It is in this tension that the investigative story unfolds, a signal that is at once a scientific object and an enigma. The next phase moves deeper, examining anomalous patterns within the pulse itself, the substructures and irregularities that may hold the key to decoding, interpretation, and understanding. These are the features that hint at purpose, revealing more than raw energy. Or closer examination of the pulse's internal patterns revealed layers of complexity that amplified its enigmatic nature. At first glance, the 12.3-second modulation was the most obvious feature, but high-resolution spectral analysis exposed subtle micro-variations within each cycle. These variations were neither uniform nor random. They followed a quasi-periodic structure that repeated with remarkable fidelity across successive pulses. Each subpulse carried minor energy deviations, shifts in phase, and microfrequency offsets, forming a hierarchy of signal elements that suggested multi-layered encoding. Fourier decomposition of the pulse revealed that these microvariations were not noise artifacts. The sidebands, separated by intervals of approximately 0.17 Hz, consistently recurred across multiple observatories. Their persistence, even when filtered for known interference sources, indicated a deliberate signature embedded within the primary pulse. It is as if the signal carries nested messages, a primary carrier delivering a general pattern, with secondary components providing more intricate data. Temporal mapping of these anomalies further deepened the mystery. Each sequence within the 12.3-second cycle displayed subtle shifts over time, suggesting adaptive behavior. The pulse is not rigid, it evolves in small controlled increments. These changes are too regular to be random, yet they do not correspond to any known orbital, rotational, or gravitational cycle of 3E Atlas. The implication is that the signal may be dynamic, potentially encoding information in a form that unfolds over extended periods. Polarization anomalies also emerged as a critical feature. While the main pulse exhibited linear polarization aligned with 3I Atlas's rotation plane, the subpulses contained alternating orientations. This alternating polarization pattern is subtle but measurable, suggesting a deliberate mechanism for modulating the signal in 3 dimensions. In practical terms, it could allow for additional data channels, increasing the potential information density of the pulse without altering the primary carrier frequency. Comparisons with previous 3I Atlas anomalies reveal a pattern of increasing sophistication. Earlier observations noted intermittent electromagnetic emissions, but none exhibited this nested multi-scale structure. The current pulse appears to represent a significant escalation, as if the object is now engaging in a form of deliberate structured communication that builds upon prior phenomena. Each anomalous layer adds a new dimension to the puzzle, making the signal progressively harder to classify as purely natural. Entropy analysis provides additional insight. While the overall pulse exhibits low randomness, consistent with intentional design, the microvariations maintain a level of complexity that resists simple decoding. This balance between order and variability is striking, resembling encoding strategies employed in advanced communication systems. The signal is structured to be detectable and repeatable, yet deliberately complex enough to prevent straightforward interpretation. Energy distribution within the pulse adds another layer of intrigue. Subpulses carry measurable energy differentials, enough to suggest active modulation rather than passive emission. These variations are consistent across independent observations, reinforcing the conclusion that the pulse is not a stochastic phenomenon. The energy profile implies control over the emission mechanism at scales far beyond conventional expectations for a naturally occurring body. From an observational standpoint, the anomalies challenge conventional analytical models. Standard astrophysical frameworks, pulsar dynamics, magnetospheric oscillations, or plasma interactions cannot replicate the nested structures observed. Each sublayer, each microvariation, seems optimized for coherent transmission, implying that the signal is designed with awareness of the intervening interstellar medium and the need for detectability at Earth taken together. These anomalous patterns suggest intentionality, adaptive modulation, and multidimensional structure. They point to a mechanism, natural, artificial, or hybrid, that is capable of producing signals far more sophisticated than previously recorded. The signal's behavior hints at purpose embedded within physics itself, raising profound questions about the nature of 3I Atlas, the mechanisms behind the pulse, and the potential for interpreting it as a form of communication. The next logical stage in this investigation is historical context, situating the pulse within the broader timeline of 3I Atlas observations. Understanding past anomalies and their evolution helps frame the current signal, providing insight into whether this event is an escalation, an isolated occurrence, or part of a longer pattern of emergent phenomena frequency, suggesting intention embedded within physics. Placing the current pulse in historical context reveals a pattern of increasingly anomalous behavior by 3I Atlas over the past decade. Initial observations dating back to early 2015 documented minor electromagnetic fluctuations, brief spikes at microwave frequencies, often dismissed as instrumental noise or minor interactions with solar radiation. These early events were subtle, unremarkable in isolation, but when logged sequentially, they formed a record of recurring anomalies centered around the object. By 2018, 3I Atlas had begun exhibiting more pronounced activity. Observatories detected intermittent bursts across the 1 to 6 GHz range, often with irregular amplitude patterns and transient polarization shifts. While still insufficient to confirm any artificial origin, the data hinted at underlying complexity, a behavior inconsistent with typical asteroid or small body electromagnetic emissions. The periodicity of some bursts suggested internal mechanisms or interactions with charged particles in its immediate environment. Between 2020 and 2023, the anomaly record expanded dramatically. Instruments documented coherent micropulses within broader emissions, a subtle precursor to the structured signal observed now. Thermal mapping revealed minor hotspots on the object's surface, localized and transient, correlating loosely with detected emissions. These signals were analyzed extensively, yet the absence of repetition or consistency left scientists unable to assert definitive patterns. Even so, the data pointed to something more than passive interaction. 3I Atlas seemed to display a form of emergent behavior, producing outputs that suggested regulation or control. The pulse detected on November 12, 2025 represents the culmination of these incremental developments. Unlike earlier bursts, it is highly structured, repeatable, and energetically coherent. What was once irregular and ambiguous has now become unmistakable, a measurable signal aligned precisely with Earth, exhibiting complex modulation and nested substructures. Historical comparison emphasizes how unprecedented this is. The anomaly has transitioned from sporadic, weak emissions to a deliberate detectable transmission that cannot be ignored. This historical trajectory also shapes interpretation. Previous anomalies, once considered minor, gain new significance in light of the current pulse. They may represent a developmental sequence, a gradual escalation of 3I Atlas's capacity for signal generation or communication. Viewed through this lens, the current event is not isolated, but part of a continuum, a series of emergent behaviors culminating in a detectable structured emission. Moreover, historical data provide benchmarks for modeling. Scientists can now analyze trends in frequency, polarization, and amplitude over time, seeking correlations with orbital positions, rotational phases, or other physical characteristics of 3I Atlas. Patterns that were previously buried in noise now take on potential significance. For instance, minor polarizations observed in 2022 align with secondary polarization components of the current pulse, suggesting continuity in modulation strategies. The historical context also underscores the growing challenge of interpretation. Each anomaly in the record has added layers of complexity, raising questions about natural processes, the object's composition, and potential mechanisms for signal generation. Early explanations, random particle interactions, solar wind-induced emissions, or minor magnetic anomalies lose credibility as the evidence accumulates. The pulse today represents a threshold, a point where accumulated anomalies demand serious consideration of artificial or hybrid mechanisms. Furthermore, comparing past and present observations offers insight into the potential intelligence or control involved. Repetition of certain features, adaptive modulation, and alignment with Earth are unlikely to result from chance. Historical context suggests that 3I Atlas has evolved, or at least exhibits behaviors over time, that are consistent with systems capable of learning, adjustment, or purposeful emission. Whether this reflects conscious design, emergent physics, or unknown natural processes remains the subject of intense investigation. This perspective leads directly into scientific debate, where experts dissect hypotheses, challenge assumptions, and weigh the plausibility of artificial versus natural explanations. By situating the current signal within its historical framework, the conversation is no longer abstract. It is rooted in measurable, chronological evidence, creating a foundation for rigorous inquiry. Scientific debate erupted almost immediately following confirmation of the pulse. Across institutions, experts dissected the evidence, weighing competing hypotheses while avoiding premature conclusions. The central tension lay between conventional astrophysics and the possibility of an artificial source, a line of inquiry fraught with both intrigue and caution. Proponents of a natural explanation pointed to potential unknown physical processes. Some suggested that 3I Atlas might possess internal electromagnetic phenomena, perhaps driven by unique mineral compositions interacting with cosmic radiation or micromagnetic fields. Others proposed exotic plasma interactions in the surrounding space environment, which could produce coherent emissions under specific conditions. These explanations, however, struggle to account for the narrowband frequency, stable polarization, and nested substructures observed in the pulse. Each model could replicate fragments of the data, yet none reproduced the full complexity without invoking improbable coincidences. At the same time, a subset of researchers argued that the signal structure and consistency strongly suggest intentionality. The regular 12.3-second modulation, the micropulse hierarchy, and adaptive polarization patterns could represent a form of engineered communication. Analysts drew analogies to known human communication systems, layered encoding, multi-channel modulation, and frequency alignment for optimal long-distance transmission. Even without decoding the content, the signal's characteristics resemble protocols designed for intentional information transfer. Methodology became a key point of contention. Some scientists cautioned that human pattern recognition bias might lead to overinterpretation. Our brains naturally seek order in randomness, and what appears structured could, in principle, emerge from chaotic interactions within an unobserved natural system. To mitigate this, independent teams applied machine learning algorithms trained to differentiate natural and artificial signals. These models consistently flagged the pulse as anomalous and non-natural, though the algorithms themselves cannot assert intent, only statistical improbability. The debate extended to energy considerations. The pulse's sustained amplitude and coherence imply a source capable of concentrating significant energy precisely across interstellar distances. If the signal is natural, 3I Atlas must harbour an unprecedented internal energy mechanism or interaction with external fields. If artificial, it suggests engineering far beyond contemporary human capabilities, raising questions about the object's origin, composition, and potential control systems. Even within artificial source hypotheses, discussion diverged. Some scientists explored the possibility of a self-organizing natural system, producing structured emissions, a hybrid explanation blending physics with emergent complexity. Others proposed intelligent design scenarios, ranging from autonomous probes to advanced extraterrestrial technologies. Each scenario carries profound implications, yet all remain speculative due to the lack of a decipherable message within the pulse. Peer review occurred in near real time. Teams exchanged datasets and independent analyses, challenging assumptions and testing model robustness. Discrepancies were small but instructive. Minor phase shifts, energy variations, or microfrequency offsets provided insight into either observational limitations or subtle signal dynamics. The rigor of debate ensures that any consensus, if achieved, will be grounded in the full breadth of observational evidence. The result is a landscape of competing theories, each with merit and limitations. Natural explanations must account for extraordinary structure. Artificial explanations must confront energy requirements and coding complexity. The debate is iterative, building with every new dataset, and no single model yet dominates. What is undeniable, however, is that the pulse cannot be dismissed. Its presence challenges existing frameworks, demands multidisciplinary expertise, and drives the global scientific community into uncharted territory. This ongoing discourse sets the stage for technological implications, where the focus shifts from interpretation to what such a signal suggests about 3I Atlas's capabilities, potential mechanisms, and the broader questions raised by a structured, detectable emission in our vicinity. The technological implications of the pulse are as striking as its scientific anomaly. Any system capable of producing a coherent, narrowly confined, and structured signal at interstellar distances must possess capabilities far beyond what is observed in natural small bodies. The energy requirements alone are considerable. Sustaining the pulse across millions of kilometers with minimal dispersion implies either an extraordinary internal energy source or a mechanism for channeling existing cosmic energy efficiently and precisely. The directional stability of the signal suggests advanced orientation control. Unlike random emissions, which radiate isotropically, the pulse maintains alignment with Earth's position, compensating for relative motion between the observer and 3i Atlas. This implies either dynamic targeting systems or an inherent physical property that stabilizes emission directionality, again, something unprecedented for a non-artificial object. Moreover, the nested subpulses and adaptive modulation hint at sophisticated information handling capability. Within human-engineered systems, such multi-layered encoding is used to maximize data transmission efficiency, error correction, and resilience against interference. If 3i Atlas is producing such structures naturally, it represents a previously unknown physical process with remarkable precision. If artificial, the object possesses computational or regulatory systems capable of managing complex signal dynamics autonomously. The scale of technological sophistication implied is staggering. For energy, orientation, and modulation to be maintained simultaneously over the pulse's observed duration, the object must either harness extreme local forces or operate a system designed with intelligence, intentionality, and adaptability. Every additional layer of the pulse, phase shifts, micropulses, polarization variations, adds to the implied complexity of the underlying mechanism. These observations raise immediate questions about the internal composition and structural design of 3i Atlas. Could the object contain materials capable of generating or amplifying electromagnetic emissions? Are there mechanisms akin to antenna arrays, resonators, or energy storage systems embedded within it? Such speculations verge into the unknown, yet the signal's sophistication cannot be reconciled with conventional asteroid or comet models. Beyond internal mechanics, the pulse challenges our understanding of long-distance communication physics. Interstellar transmission over millions of kilometers without dispersion, while maintaining coherent microstructures, implies either compensation for or immunity to interstellar plasma effects, magnetic interference, and cosmic background noise. For human technology, this would require dynamic correction systems or exotic transmission methods. For 3i Atlas, it suggests that such mechanisms, whether natural or engineered, already exist within the object. The technological stakes are further heightened by the pulse's adaptability. Minor variations in timing, phase, and energy suggest either an evolving signal or responsive modulation. If these changes are deliberate, 3i Atlas may be adjusting its emission in real time, potentially reacting to observation, orbital conditions, or other unknown parameters. This would elevate the object from a passive emitter to an active participant in communication, or at least an autonomous system capable of maintaining complex adaptive outputs. These implications ripple outward. Any civilization or system capable of producing such emissions would operate at a technological threshold beyond current human understanding. Even if natural processes are ultimately responsible, the physics involved suggests new mechanisms for energy concentration, signal coherence, and directional control. In either scenario, the pulse forces reconsideration of assumptions regarding small body capabilities, electromagnetic phenomena, and interstellar communication strategies. As the investigation continues, attention expands beyond raw observation. Researchers now analyze potential mechanisms, model energy transfer, and simulate how nested modulations could be produced and maintained. Understanding the technological implications not only informs interpretation of the current signal, but also frames future monitoring strategies, as any recurrence or variation will shed further light on the object's capabilities. The next step in the investigation turns to cross-disciplinary inquiry, integrating astrophysics, geophysics, signal processing, and computational modeling to build a holistic understanding of the pulse, its origins, and its implications. Cross-disciplinary inquiry has become essential in understanding the 3i Atlas pulse. No single field can account for the range of observed phenomena. Astrophysics, geophysics, signal processing, and computational modeling must converge to create a coherent framework. Each discipline contributes a unique lens, revealing dimensions of the signal invisible to others, Astrophysicists focus on the broader cosmic context. They analyse how 3I Atlas interacts with solar radiation, the interplanetary magnetic field, and cosmic rays. These interactions could, in theory, induce electromagnetic effects, but models consistently fail to replicate the signal's precise frequency, modulation, and nested structure. Astrophysics provides boundary conditions defining what is physically plausible and highlighting where anomalies exceed natural expectation. Geophysicists and planetary scientists examine material and structural possibilities. Could 3I Atlas's composition, its mineral content, density variations, or internal layering produce or amplify electromagnetic emissions? Thermal mapping, radar tomography, and spectroscopic data are integrated to explore potential resonance effects or energy storage mechanisms. While some localized interactions are possible, none account for the combination of coherence, energy, and adaptive modulation seen in the pulse. Signal processing experts decode what can be observed without assuming content. They dissect frequency components, analyze phase shifts, and model potential encoding strategies. Advanced algorithms, including neural networks trained on both natural and artificial signal datasets, identify patterns invisible to conventional methods. These analyses confirm that the pulse exhibits multi-layered structuring optimized for detectability and potential information density, further differentiating it from stochastic cosmic noise. Computational modelers attempt to bridge theory and observation, simulating scenarios that integrate physics, signal theory, and potential energy sources. Their models explore energy amplification, modulation propagation, and stability of directional transmission. Even under optimized parameters, reproducing the observed pulse without some form of active regulation or intelligent design proves extraordinarily difficult. These simulations highlight gaps in current understanding, emphasizing the need for novel theoretical frameworks. Collaboration across disciplines has also revealed subtle correlations. For example, polarization anomalies correspond with material distribution patterns, while micropulse timing appears linked to rotational dynamics in unexpected ways. These intersections, invisible in isolated studies, suggest the pulse may involve complex coupling between physical structure and emission mechanism, a synergy that is at once natural in process yet artificial in effect. Data integration platforms now allow near real-time synthesis of observations, feeding multispectral and multi-temporal data into unified models. This approach enables scientists to test hypotheses against the full dataset rather than isolated observations. Each iteration refines understanding, ruling out some scenarios while elevating the plausibility of others. Adaptive modeling reveals that minor variations in pulse characteristics could be responses to orbital position or observational interference, hinting at a system capable of environmental calibration. This holistic approach demonstrates that understanding the 3I Atlas pulse cannot rely on single-discipline analysis. It is a phenomenon that spans the physical, computational, and theoretical, defying conventional classification. The pulse exists as both signal and system, demanding investigation that simultaneously accounts for natural physics, emergent complexity, and potential intelligence. The outcome of cross-disciplinary inquiry sets the stage for examining the institutional and public response, where the combination of rigorous scientific investigation and the extraordinary nature of the anomaly triggers coordinated global attention. The discovery of the pulse did not remain confined to academic circles for long. Within hours, international space agencies, government observatories, and scientific institutions had been alerted, triggering a coordinated response. The event, though not officially declared a crisis, commanded immediate scrutiny. Communication protocols were enacted to ensure data integrity and prevent misinterpretation, while observatories around the globe synchronized observations to track the pulse continuously. Scientific institutions prioritized verification. Redundant measurements were performed, cross-referencing terrestrial arrays with space-based instruments. Data sharing protocols were accelerated, with secure channels established to prevent contamination, duplication errors, or premature public speculation. The process resembled a high-stakes operation, balancing transparency within the scientific community against the need for caution. International coordination became essential. Observatories in Europe, North America, East Asia, and Australia shared not only raw measurements but also real-time analyses. Conferences and emergency briefings took place virtually, integrating findings from specialists in astrophysics, signal processing, and planetary science. Each new observation informed a dynamic, evolving understanding of the pulse, emphasizing its consistency, reproducibility, and complexity. Government agencies monitored the situation for potential implications beyond science. While there was no immediate threat to Earth, the possibility of receiving a structured signal from an interstellar object carries strategic and technological significance. Analysts considered scenarios ranging from natural astrophysical phenomena to unprecedented technological artifacts, evaluating what measures, scientific, observational, or precautionary, might be required. Public awareness remained tightly controlled. Early communications emphasized the extraordinary nature of the signal without asserting conclusions. This careful messaging preserved both credibility and analytical focus, preventing speculation from overwhelming the data-driven investigation. Nevertheless, media and scientific outlets began reporting on the pulse's detection, prompting curiosity, debate, and cautious excitement across the global audience. Institutional responses also included enhanced monitoring. Additional instruments, previously reserved for specialized studies, were repurposed to track 3-eye atlas high-resolution spectrometry. Adaptive optics imaging and real-time computational modeling were deployed to capture every nuance of the pulse. This unprecedented observational effort represents a global scientific mobilization, reflecting both the rarity of the event and the potential significance of the signal. At the same time, protocols for data interpretation were formalized. Teams established verification hierarchies, cross-checking each dataset against independent models, while committees reviewed preliminary analyses before circulation. The pulse's consistency across instruments, along with its multi-layered structure, left little room for misclassification, but the possibility of error remained a guiding principle in all institutional decision-making. This coordinated response also underscores the gravity of the anomaly within scientific frameworks. It is rare for a single object, particularly a small body like 3-eye atlas, to command such sustained multidisciplinary attention. The combination of detectable energy, structured modulation, and repeatable timing elevates the pulse from curiosity to central focus, demanding a level of scrutiny and cooperation comparable to other high-profile astronomical events. By examining the institutional and public response, it becomes clear that the pulse is not just a technical anomaly, it is a catalyst for global scientific engagement. The event has mobilized expertise, resources, and observational infrastructure on a scale rarely seen, laying the foundation for the next stage of investigation, tracing the pulse's timeline, reconstructing its emergence, and understanding how it behaves over time. Reconstructing the pulse's timeline provides critical insight into both its origin and behavior. By collating data from multiple observatories and instruments, analysts were able to map the sequence of events leading to the November 12th detection with remarkable precision. The pulse was not a single occurrence. Rather, it exhibited subtle precursors and variations spanning days and weeks prior. Archived data revealed that minor, previously overlooked emissions occurred at irregular intervals over the previous month. These weak pulses, initially dismissed as background noise, displayed nascent versions of the modulation patterns now observed in the main signal. Their frequencies hovered around 4.19 GHz, and their amplitude variations hinted at the 12.3 second cycle, though inconsistently in retrospect, these precursor pulses represent early manifestations of the system now producing coherent structured transmissions. The main pulse, detected at 3:17 UTC, marked a threshold. Its amplitude increased sharply over a period of several minutes, stabilizing into a steady, repeatable rhythm. This rapid transition suggests either a sudden activation of a mechanism within 3-eye atlas, or the culmination of a process that had been building over time. Observatories noted that minor fluctuations within the micropulses persisted throughout the early phase, indicating ongoing adaptation or fine-tuning subsequent pulses maintained consistency for hours, with only minute phase variations. These slight deviations are significant. They may represent environmental adjustments, signal calibration, or an intrinsic characteristic of the emission process. The stability of the pulse over extended duration is itself anomalous. Natural astrophysical sources rarely sustain such precision over hours without detectable dispersion or amplitude, decay, temporal correlation with 3-eye atlas's rotation, and orbital position revealed further complexity. The pulse's primary modulation cycle did not align perfectly with the object's rotational period, suggesting that the emission mechanism is decoupled from simple mechanical or rotational drivers. This decoupling strengthens the argument for an active or regulated process, whether artificial or emergent, that maintains signal coherence independent of the body's movement. High-resolution timing analysis exposed secondary cycles embedded within the primary 12.3-second modulation. These subcycles, lasting fractions of a second, repeat with slight variations across successive primary cycles, forming a layered temporal hierarchy. Such structuring is rare in naturally occurring emissions and hints at sophisticated control, possibly encoding information or implementing error correction protocols across the pulse sequence. Over the span of the observation period, the pulse demonstrated subtle evolution. Energy distribution, micropulse timing, and polarization components shifted incrementally. While the changes are small, they are measurable and consistent across independent observatories. This adaptive behavior is not consistent with random fluctuation or transient cosmic events, and it suggests a dynamic system capable of regulating its output in real time. Reconstructing the timeline also highlights gaps and uncertainties. Some precursor emissions may have gone undetected due to instrument sensitivity limits, while environmental interference occasionally masked minor features. Nevertheless, the cumulative record establishes a clear trajectory, from weak, intermittent anomalies to a fully coherent, structured pulse observable across the globe. This timeline provides a framework for understanding the pulse's evolution, revealing that what was initially subtle has escalated into a sustained, complex, and measurable phenomenon. It also sets the stage for exploring alternative explanations, evaluating whether natural, artificial, or hybrid mechanisms best account for the observed behaviors and temporal dynamics. Alternative explanations for the 3i Atlas pulse have been subjected to rigorous scrutiny, each evaluated against the growing body of observational data. Broadly, hypotheses fall into three categories: natural astrophysical processes, artificial mechanisms, and hybrid scenarios, blending emergent physics with structural complexity. Natural explanations focus on phenomena traditionally observed in small bodies, plasma interactions, and cosmic radiation. Some propose that internal magnetohydrodynamic processes could generate coherent emissions under rare conditions, perhaps linked to charged particle dynamics or internal resonance within 3i Atlas's mineral composition. Others consider interactions with the solar wind or interplanetary magnetic fields, where alignment or amplification could produce periodic pulses. However, these models struggle to reproduce the signal's narrowband frequency, persistent polarization, layered sub-pulses, and precise directional targeting toward Earth. Each attempt accounts for a fragment of the behavior, but fails to encompass the full set of anomalies simultaneously. Artificial source hypotheses draw attention to the structured nature of the signal. The nested micropulses, modulation cycles, and adaptive polarization are reminiscent of advanced communication protocols. In human-engineered systems, similar patterns are used to maximize data density, maintain coherence across noisy channels, and correct for transmission errors. If 3i Atlas is producing such structured emissions intentionally, the object would possess systems capable of energy concentration, directional alignment, and real-time modulation, capabilities far beyond conventional small-body behavior. These mechanisms, if artificial, suggest either autonomous engineering or an intelligent process embedded within the object. Hybrid explanations explore the intersection of natural and artificial processes. In these scenarios, a natural structure or phenomenon within 3i Atlas could act as a substrate, while adaptive processes, potentially emergent, self-organizing, or externally triggered, impart structured modulation. Such models attempt to reconcile extraordinary signal complexity with plausible physical mechanisms, suggesting that some form of regulation could emerge naturally or through interaction with unknown cosmic forces. While compelling, hybrid explanations remain speculative, requiring physics not yet fully understood or observed elsewhere in the solar system. Comparative analysis provides further clarity. Past anomalies, thermal hotspots, and electromagnetic spikes hint at incremental development within 3i Atlas, suggesting that whatever mechanism is responsible has evolved or intensified over time. The pulse is the first instance where the system demonstrates full, coherent, and repeatable emissions at Earth-detectable levels. This escalation is difficult to reconcile with purely random natural processes, lending weight to hypotheses that involve controlled or self-organizing mechanisms. Energy requirements and spatial targeting reinforce constraints. Producing a coherent signal across millions of kilometers without substantial dispersion demands precise control over both amplitude and direction. Natural emissions rarely maintain such precision over long durations, while artificial systems are specifically designed to achieve it. The pulse's nested structures and adaptive microvariations further imply real-time regulation, adaptive feedback, or an intrinsic self-correcting process. Any viable explanation must account for these combined phenomena. Critically, none of these alternatives has been conclusively confirmed. Each offers partial insight but leaves significant questions unanswered: how the energy is sourced, how modulation is maintained, and why the pulse targets Earth specifically. The lack of a decipherable message, despite structured complexity, limits interpretive certainty, leaving a central tension between observable evidence and the need for theoretical explanation. This stage in analysis highlights both the extraordinary nature of the pulse and the limits of current understanding. By systematically evaluating natural, artificial, and hybrid explanations, scientists can eliminate unlikely scenarios while refining models to account for observed data. Yet each hypothesis carries implications that extend beyond physics into questions of potential intelligence, emergent systems, or previously unknown cosmic mechanisms. The discussion of alternative explanations sets the stage for examining signal decoding and information analysis, the next step in which researchers attempt to extract meaning, or at least identifiable structure, from the complex multi-layered pulse. Signal decoding and information analysis represent the most intricate phase of the investigation. With the pulse exhibiting nested micropulses, adaptive modulation, and precise polarization, researchers treat the signal as potentially carrying structured information, even if its encoding method is unlike any terrestrial system. Initial steps focused on mapping the pulse in multiple domains simultaneously. Time-frequency analysis, combined with phase and polarization mapping, revealed recurring patterns across scales. Each 12.3-second cycle contained substructures that repeated with slight, controlled variation, suggesting either error-correcting protocols or hierarchical encoding. These patterns were analyzed statistically, using entropy measures and correlation matrices, to determine whether the variations were stochastic or deliberately structured. Results consistently indicated low entropy at multiple scales, signaling deliberate organization rather than random fluctuation. Researchers then applied comparative modeling. Analogues were drawn from known communication protocols, binary sequences, prime number spacing, and multi-level amplitude modulation. While no human-readable content emerged, these comparisons helped define structural motifs within the signal. Certain subpulses exhibited ratios reminiscent of prime sequences or Fibonacci-like intervals, which are often proposed as universal markers of intelligent origin. Whether these ratios serve communicative, self-regulating, or entirely physical purposes remains unresolved. Cross-observatory verification proved essential. Each telescope captured subtle variations in micropulse timing and phase. By synthesizing these datasets, analysts reconstructed a high-fidelity temporal map, revealing a hierarchical organization, primary cycles, secondary micropulses, and tertiary fluctuations. The stability and repetition across independent measurements confirmed that the structure is intrinsic to the signal, rather than an artifact of detection or environmental interference. Polarization encoding presented another layer. The main pulse maintained linear polarization aligned with 3I Atlas's rotational plane, but subpulses alternated orientation in consistent, measurable patterns. This suggests a multi-channel communication method or an adaptive emission system capable of conveying additional data dimensions. In human engineering, polarization modulation is used to increase information capacity without altering frequency, an advanced technique that may have parallels here, whether natural or artificial. Attempts at pattern recognition leveraged machine learning, including unsupervised neural networks trained to detect non-random sequences in complex signals. These models identified recurring motifs, phase relationships, and amplitude ratios invisible to conventional analysis. While interpretation remains elusive, The ability to isolate these motifs suggests that the pulse is far from random and may contain structured content awaiting decipherment. Energy distribution within the micropulses also factors into decoding attempts. Slight variations in amplitude appear systematic, potentially encoding information in intensity rather than timing alone. By modelling these amplitude shifts as a parallel channel of data, researchers have begun constructing multi-layered signal maps, where timing, frequency, phase, polarization, and energy collectively define a potential information structure. Despite these advances, decoding remains incomplete. The encoding scheme, if indeed intentional, is unfamiliar. Human systems rely on known symbolic, mathematical, or linguistic frameworks, while the pulse may employ methods entirely alien to our understanding. Nevertheless, even without direct interpretation, the signal provides measurable complexity and hierarchy, indicating purposeful structuring rather than random emission. This phase underscores both progress and limits. Analysis has confirmed the pulse's layered architecture, validated its reproducibility, and identified features consistent with information-bearing systems. Yet the content, if it exists, is beyond current decoding capacity. The challenge now is to expand both observational and computational methods, integrating new data streams, refining models, and exploring whether the signal's structure reveals universal principles of communication or entirely novel mechanisms. The next stage naturally advances to interstellar implications, exploring how this pulse reshapes understanding of small body phenomena, potential intelligent signals, and the broader context of communication across cosmic distances. The interstellar implications of the 3i Atlas pulse extend far beyond its immediate detection. For decades, astronomers have observed distant emissions, pulsars, fast radio bursts, magnetar flares, but never with the combination of structure, coherence, and target-specific alignment now exhibited. The pulse challenges assumptions about what small bodies can do, and more broadly about the limits of signal generation and propagation across interstellar space. One immediate implication concerns detectability. If 3i Atlas can produce a coherent signal observable across millions of kilometers, it demonstrates that interstellar communication may not require massive megastructures or high-energy lasers. Smaller objects, given the right physical properties or internal mechanisms, could serve as platforms for precise emission. This expands the range of potential natural or artificial sources capable of signaling across the cosmos, forcing a re-evaluation of search strategies for extraterrestrial intelligence. Another consideration is the universality of signal design. The pulse's modulation, polarization, and nested substructures suggest methods optimized for clarity across interstellar media. If this represents an intentional communication strategy, it implies knowledge of propagation physics, noise mitigation, and detection limits. Whether produced by natural processes or intelligent systems, the signal reflects a system operating with principles that transcend human-engineered methods. The underlying physics, energy concentration, directional stability, adaptive modulation, offers insights that could inform future technological development on Earth, both in communication and in observational instrumentation. Propagation over interstellar distances also raises questions about medium interaction. The pulse maintains coherence despite travelling through charged particle fields, magnetic turbulence, and cosmic radiation. For naturally generated pulses, this implies unknown mechanisms for dispersion mitigation or self-stabilization. For artificial or hybrid mechanisms, it demonstrates a level of control sufficient to maintain signal integrity over vast distances, which itself constitutes a technological marvel. The observed adaptation within micropulses may represent a dynamic response to interstellar interference, analogous to error correction in advanced communication systems. Furthermore, the pulse prompts reconsideration of object classification. 3i Atlas has long been catalogued as a small body, but its emission properties suggest capabilities normally reserved for engineered or anomalous astrophysical objects. The interstellar implication is profound. Classification based solely on size, orbit, or composition may overlook functional complexity, masking phenomena that operate outside conventional categories. If other small bodies possess similar capabilities, the universe may harbour a broader range of signal-emitting objects than previously considered. The interstellar context also affects the probability calculations for detection. Earth-based observers are fortunate in alignment and timing. If the pulse is periodic or adaptive, the likelihood of detecting similar signals elsewhere increases, prompting a reassessment of observational strategies and resource allocation for SETI-style monitoring. Conversely, the specificity of alignment may suggest that such signals are rare or purposefully targeted, highlighting the significance of 3E Atlas's current orientation relative to Earth. Finally, the pulse challenges assumptions about temporal evolution. Historical observations of 3I Atlas indicate incremental development in emission behavior. Interstellar signals may not be static but evolve over time, reflecting adaptive processes, environmental interactions, or intentional modulation changes. Recognizing this dynamism reshapes expectations for signal detection, interpretation, and analysis across the galaxy. Taken together, the interstellar implications are both practical and philosophical. The pulse demands reconsideration of astrophysical norms, challenges the limits of natural and artificial mechanisms, and opens new frontiers in the search for cosmic communication. It situates 3I Atlas not merely as an isolated anomaly, but as a focal point for understanding how structured emissions might manifest and propagate across vast cosmic distances. The next stage in this unfolding investigation examines predictive modelling, assessing how future pulses might behave, what parameters can be anticipated, and how monitoring strategies can adapt to evolving signals. ChatGPT said, "Predictive modelling has become a central focus as scientists attempt to anticipate the behaviour of 3I Atlas's pulse. By integrating historical data, current observations, and cross-disciplinary analysis, researchers aim to construct models capable of forecasting future emissions, their timing, structure, and potential variations. The goal is not only to observe but to prepare, optimizing instruments and analytical frameworks to capture the full richness of subsequent pulses." The modelling process begins with empirical patterns. The 12.3-second primary cycle, the nested micropulses, and adaptive polarization provide measurable constants. By analysing these features across multiple observation windows, scientists identify trends, minor phase shifts, and amplitude variations. These trends form the foundation of predictive algorithms, allowing simulations to project how pulses might evolve over hours, days, or even weeks. Physical parameters of 3I Atlas are integrated into the models. Rotational dynamics, surface composition, magnetic field distribution, and orbital motion all influence pulse characteristics. By coupling these variables with known environmental factors, solar wind, cosmic radiation, interplanetary magnetic fluctuations, researchers refine projections, isolating components intrinsic to the object from those influenced by external conditions. This dual-layer modelling helps determine whether observed adaptations are internally generated or responses to the surrounding environment. Statistical methods augment these simulations. Probabilistic forecasting accounts for subtle deviations in micropulse timing, energy distribution, and polarization patterns. While the overall structure is highly repeatable, minor variations persist, suggesting either environmental modulation or intrinsic regulation. Predictive models incorporate these stochastic elements, producing ranges of expected outcomes rather than rigid forecasts. This approach ensures that monitoring systems remain sensitive to anomalies that deviate slightly from prior pulses, but still fit within the broader structural framework. Machine learning algorithms have proven particularly effective. Neural networks trained on historical data identify latent patterns not immediately apparent to human analysts. These models can simulate potential sequences of pulse evolution, anticipate micropulse adjustments, and highlight features likely to repeat or transform in future emissions. Although interpretation remains uncertain, these forecasts guide instrument calibration and observational priorities, ensuring that no critical nuance is overlooked. Energy modelling also plays a key role. By estimating the power distribution within primary and secondary subpulses, researchers can predict amplitude fluctuations, potential saturation points, and the thresholds at which pulse features might shift. Understanding energy dynamics informs expectations about the pulse's persistence, its possible decay over time, and the constraints on signal generation mechanisms, whether natural, artificial, or hybrid. Predictive modelling also considers external detection factors. Earth-based observatories experience varying sensitivity depending on atmospheric conditions, alignment, and instrumental limitations. Models integrate these constraints, simulating what the pulse would appear like across different observational platforms, This multi-layered approach ensures that anticipated variations are not mistaken for signal anomalies or misinterpretations, refining both observational strategy and scientific inference. Finally, predictive modelling informs broader investigation planning. By anticipating when and how the pulse might evolve, scientists can optimise data collection, coordinate global observation campaigns, and prioritise computational resources for real-time analysis. Each predicted pulse provides an opportunity to test models against reality, iteratively refining understanding and gradually constraining hypotheses about the mechanisms behind 3I Atlas's emissions. This modelling phase naturally leads into the study of potential cosmic interactions, examining how the pulse and 3I Atlas might interact with surrounding space environments, planetary magnetospheres, or interstellar media, potentially revealing further clues about the nature of the signal and its propagation. Potential cosmic interactions add another layer of complexity to understanding the 3I Atlas pulse. As the signal propagates through space, it encounters a variety of environments that could influence its structure, coherence, and detectability. Interstellar medium, solar wind, magnetic fields, and planetary magnetospheres all interact with electromagnetic emissions, sometimes subtly, sometimes profoundly, altering both amplitude and frequency. Analysis of the pulse's interaction with the interplanetary medium reveals remarkable resilience. Over millions of kilometers, the primary modulation cycle remains coherent, and micropulse structures persist without significant distortion. This suggests either extraordinary signal stability or active compensation mechanisms within the emission process. Natural processes, like plasma dispersion or magnetic turbulence, typically introduce frequency-dependent delays or phase shifts, yet these effects appear minimal in the observed pulse. The implication is that 3I Atlas either inherently stabilizes emissions or possesses an unknown mechanism mitigating environmental interference. Polarization studies further illuminate interactions. Variations in sub-pulse polarization seem to respond to local magnetic field orientation, albeit subtly. This could indicate that the pulse is sensitive to its environment, either by design or through physical coupling. Adaptive polarization could serve multiple purposes: maintaining coherence, encoding additional information, or enhancing detectability across variable interstellar conditions. The precision observed implies a system finely tuned to the physics of space between the object and Earth. Nearby planetary magnetospheres may also play a role. While 3I Atlas's trajectory keeps it far from major bodies, occasional proximity to smaller planetary magnetic fields could influence signal propagation. Modelling these interactions shows that minor shifts in frequency or phase could result from such encounters, potentially explaining some of the micropulse variability observed. These environmental interactions do not undermine the pulse's coherence, but instead highlight its dynamic stability under real-world conditions. Cosmic ray fluxes, charged particle densities, and solar activity cycles also factor into pulse behavior. Statistical correlation between minor solar events and micropulse deviations suggests that 3I Atlas's emission mechanism, or its signal path, is sensitive to fluctuations in charged particle environments. The object's pulse appears robust yet subtly responsive, a combination of resilience and adaptability rarely observed in naturally occurring emissions from small bodies. Interstellar medium interactions are particularly revealing. Signal modelling indicates that dispersion, scattering, and absorption effects are minimal for the 4.19 GHz carrier frequency, yet micropulse structures could be more vulnerable. The persistence of these structures implies that either the emission mechanism anticipates medium effects, or that the signal's design inherently mitigates distortion. This resilience challenges conventional understanding of interstellar propagation, suggesting either a new physical phenomenon or highly optimized emission characteristics. Finally, potential interactions raise questions about long-term stability and detectability. If environmental factors influence micropulse features, monitoring future pulses may reveal adaptive behaviors or systematic responses. Understanding these cosmic interactions provides insight not only into the pulse's physical propagation, but also into the capabilities and sophistication of 3I Atlas itself. The study of cosmic interactions naturally leads to the next phase, deciphering broader implications, considering what the pulse means for interstellar communication, observational astronomy, and our understanding of structured emissions from small bodies. the broader implications of the 3i Atlas pulse extend beyond a single astronomical anomaly. Its presence forces a re-evaluation of assumptions about small body capabilities, interstellar communication, and the limits of naturally occurring electromagnetic phenomena. Whether produced by a natural, artificial, or hybrid mechanism, the signal challenges established paradigms. From an observational perspective, the pulse demonstrates that detectable, structured emissions can originate from relatively small celestial objects. Traditionally, interstellar communication has been associated with massive energy sources, pulsars, magnetars, or hypothetical megastructures. 3i Atlas shows that smaller bodies, under certain conditions, may also serve as viable emission platforms. This realization broadens the scope of targets for astronomers and astrobiologists, suggesting that previously overlooked objects could host or generate signals of interest. In terms of signal science, the pulse introduces a new model for complex multi-layered emissions. Its nested subpulses, adaptive polarization, and hierarchical timing offer a template for analyzing other potential signals. Even without direct decipherment, the structure provides insight into how information, or at least intentionally patterned energy, can propagate over interstellar distances. For human technology, this could inspire novel communication strategies, error correction protocols, or adaptive modulation techniques optimized for long-range transmission. The event also raises questions about the potential for intelligent origin. While no conclusive evidence of artificiality exists, the pulse's complexity, adaptability, and directional stability are consistent with engineered systems. If intelligence is involved, it may not be recognizable in familiar terms. Instead, the signal could reflect principles of communication and computation entirely alien to human experience. Yet even considering natural explanations, the mechanisms required to produce this level of structure are extraordinary, pointing to emergent behaviors or physical processes previously unobserved in small bodies. Cosmologically, the pulse emphasizes the interconnectedness of observational, theoretical, and technological domains. Each new measurement, analysis, and model contributes to a dynamic understanding of 3i Atlas, reinforcing the need for cross-disciplinary collaboration. Observations inform theory, theory guides instrumentation, and instrumentation refines subsequent measurements, creating a feedback loop that accelerates discovery while maintaining rigorous scientific standards. Finally, the pulse reframes expectations for temporal dynamics and celestial phenomena. Past anomalies in 3i Atlas suggested sporadic, weak emissions. Today, the object exhibits sustained, coherent, and adaptive outputs. This evolution underscores that interstellar signals may not be static or singular events, but dynamic phenomena with histories, emergent properties, and possibly predictive behaviors. Recognizing this complexity will shape future observation campaigns and influence how scientists interpret similar anomalies elsewhere in the galaxy. Taken together, the broader implications are profound. The pulse is not merely a signal, it is a case study in cosmic communication, a challenge to existing astrophysical models, and a reminder of how much remains unknown. Its structured complexity, adaptive micropulses, and directional alignment position 3i Atlas as a focal point for understanding interstellar signaling, emergent small-body physics, and the potential for intelligence beyond Earth. The next stage in the narrative naturally turns to long-term observation strategy, examining how ongoing monitoring will capture the evolution of the pulse and potentially reveal further layers of structure, behavior, and interaction. Long-term observation strategy has become a central component of the ongoing study of 3i Atlas. Given the pulse's complexity, adaptability, and historical evolution, continuous monitoring is essential to capture not only recurring emissions but also subtle changes that could reveal underlying mechanisms. Observatories around the globe, both terrestrial and space-based, have been integrated into a coordinated network to maximize coverage, sensitivity, and temporal resolution. This strategy emphasizes multi-wavelength observation. While the primary pulse resides around 4.19 GHz, instruments track secondary harmonics, broadband fluctuations, and polarization variations across the electromagnetic spectrum. High-resolution spectroscopy and adaptive optics imaging are deployed to identify any correlated phenomena on or near the object itself. Thermal and radar mapping complement electromagnetic monitoring, providing insight into potential structural or compositional drivers of the emissions. Redundancy and cross-validation are key priorities. By overlapping observation windows across multiple facilities, researchers minimize the risk of missed features, instrumental artifacts, or environmental interference. Data pipelines are synchronized to ensure that micropulse timing, phase alignment, and polarization metrics are precisely captured and compared. This redundancy allows subtle variations to be detected with confidence, offering clues to the emission mechanism and its potential responsiveness to external conditions. Temporal resolution is another focus. Continuous high-speed sampling enables the capture of micropulses, sub-pulse hierarchies, and adaptive fluctuations. These fine-scale measurements are critical for analyzing patterns that might otherwise appear stochastic. By maintaining minute-level or even sub-second resolution, scientists can trace pulse evolution in near real time, correlating changes with environmental factors, orbital dynamics, or rotational phases. Machine learning integration enhances long-term monitoring. Neural networks continuously process incoming data streams, identifying deviations, emergent patterns, and recurring motifs. These models adapt as new pulses are observed, improving predictive capability and guiding observational priorities. In essence, the monitoring system becomes not only a passive recorder, but an active analytical partner, flagging features likely to yield insight into the underlying process. Global coordination also addresses contingency planning. Observatories in different hemispheres compensate for Earth's rotation, weather conditions, and temporary instrument unavailability. Space-based platforms supplement terrestrial gaps, providing continuous observation when ground-based instruments are offline. This multi-layered approach ensures maximal coverage and continuity, critical for understanding both short-term variability and long-term trends. Long-term observation also supports experimental probing. By observing the pulse under varying conditions, different orbital phases, relative positions to Earth, and environmental states, scientists can test hypotheses regarding modulation mechanisms, adaptive behavior, and signal resilience. Each pulse becomes a data point not only for immediate analysis, but also for cumulative modeling, gradually building a comprehensive profile of 3 iAtlas's emission dynamics. Finally, the long-term strategy integrates archival research and predictive simulation. Historical anomalies, precursor emissions, and prior bursts are continuously reanalyzed in light of new data. Predictive models inform observation schedules, focusing attention on times and configurations most likely to produce significant features. This iterative approach ensures that long-term monitoring is both reactive and proactive, capturing real-time behavior while anticipating emergent patterns. The framework of sustained, high-resolution, multidisciplinary monitoring sets the stage for examining potential future trajectories of the pulse, where observed trends, predictive modeling, and adaptive analysis converge to forecast how 3 iAtlas might behave over weeks, months, or years, and what new phenomena may yet emerge. Potential future trajectories of the 3 iAtlas pulse present a landscape of both expectation and uncertainty. Observation suggests that the pulse may evolve along multiple axes: intensity, modulation complexity, micropulse structure, and directional targeting. Each axis provides insight into the underlying mechanism, whether natural, artificial, or hybrid, and informs the design of ongoing observation campaigns. Energy output is likely to fluctuate. Historical data indicate periods of ramp-up and stabilization, implying that the pulse is not a constant monolithic emission. Future trajectories may include gradual increases in amplitude, bursts of intensified micropulses, or brief lulls that reveal underlying cycles in the object's energy distribution. Modeling suggests that these variations could correlate with rotational dynamics, thermal cycles, or environmental interactions with solar wind and interstellar medium. Modulation complexity may deepen over time. The nested hierarchy of micropulses observed already hints at a system capable of adapting or encoding information at multiple scales. Future pulses might reveal additional sublayers, longer-term periodicities, or emergent motifs not previously detected. Each new layer would increase the sophistication of the signal, offering opportunities for pattern recognition and potential decoding, while simultaneously challenging conventional astrophysical interpretations. Directional targeting remains a critical variable. Current observations show a remarkable stability toward Earth, but minor phase shifts and microvariations suggest potential dynamic adjustment. Predictive models indicate that this alignment may persist for weeks or months, depending on orbital mechanics, rotational orientation, and possible self-regulating mechanisms within 3I Atlas. Understanding these directional dynamics is essential for long-term monitoring and for interpreting potential interactions with other celestial bodies or observation points. Polarization and phase relationships are also expected to evolve. Past micropulse analysis demonstrates subtle but measurable variation across cycles, which may continue in future emissions. These changes could reflect adaptive stabilization, environmental compensation, or emergent system behavior. Tracking these trends over extended periods will provide insight into the physical or engineered principles governing the pulse, offering indirect evidence of internal structure, feedback systems, or external modulation. Environmental interactions will continue to shape the pulse. Solar activity, interplanetary magnetic fluctuations, and cosmic radiation can introduce minor perturbations, which may reveal the pulse's resilience and potential compensatory mechanisms. Observing how 3I Atlas maintains coherence under these conditions can shed light on whether the system relies on active regulation, emergent properties, or unknown physical processes. Finally, cumulative monitoring over time may reveal long-term evolution in behavior. The pulse could exhibit periodic cycles, escalation in complexity, or unexpected transitions that challenge current predictive models. Each successive observation contributes to a temporal map, allowing scientists to refine simulations, test hypotheses, and anticipate future phenomena. The trajectory is not deterministic but probabilistic, offering opportunities to observe how complex emissions develop, stabilize, or adapt in real cosmic conditions. Understanding potential trajectories positions researchers to ask the next critical questions. How will 3I Atlas behave as it moves along its orbital path? Will micropulse structures evolve beyond current detection thresholds? Could the pulse reveal latent signals or secondary emissions previously obscured? These questions frame the ongoing investigation and set the stage for the next analytical focus, evaluating the long-term significance and potential consequences of sustained structured emissions from a small body in our solar system. Evaluating the long-term significance of 3I Atlas's sustained structured emissions reveals implications that extend well beyond the immediate scientific curiosity. For decades, the framework for understanding small bodies, asteroids, comets, and minor planets has assumed limited internal complexity and negligible capability for persistent, organized electromagnetic activity. The pulse challenges these assumptions, forcing a reconsideration of both classification and potential function. If the pulse continues over months or years, it could redefine the role small bodies play in cosmic signaling. Traditionally, structured signals were associated with stars, pulsars, or technologically active civilizations. 3I Atlas demonstrates that smaller, seemingly inert objects can also generate emissions of remarkable coherence and sophistication. Whether through natural self-organization, emergent physical phenomena, or some form of embedded technology, this suggests that the range of objects capable of detectable structured communication is broader than previously considered. Long-term persistence carries implications for observational strategy. Astronomical surveys and SETI initiatives may need to expand their scope to include small bodies, re-evaluating past observations for weak or intermittent pulses previously dismissed as noise. The identification of patterns in emissions from minor celestial objects could reveal a new class of signals that has gone undetected due to conventional biases in instrumentation or data analysis. Protocols sustained emissions also inform the study of adaptive or responsive phenomena. The micropulse hierarchy, polarization dynamics, and phase variations suggest a system capable of ongoing adjustment to internal or external conditions. Long-term monitoring could reveal whether these adaptive traits are stable, evolving, or responsive to environmental factors, providing a rare window into the mechanics of a naturally or artificially regulated system operating at interstellar scales. There are broader scientific consequences as well. The physics required to maintain coherent, structured emissions over vast distances challenges current understanding of energy concentration, signal propagation, and environmental resilience. Whether these arise from previously unobserved natural processes or engineered mechanisms, the existence of such a system expands the boundaries of what is physically plausible, and provides a rare opportunity to study mechanisms that might otherwise remain theoretical. Finally, the pulse invites reflection on the potential consequences of discovery itself. If the emissions are artificial, even in principle, they represent a point of contact with phenomena outside human experience, raising questions about detection, interpretation, and response. Even if natural, the sustained presence of such structured emissions forces a reassessment of how intelligence, emergent complexity, and information-bearing phenomena might manifest in the cosmos, reshaping long-term strategies for observation, modelling, and theoretical development. The long-term significance of 3U Atlas's pulse thus extends across multiple domains: scientific, observational, technological, and philosophical. Its persistence transforms it from a transient anomaly into a continuous object of inquiry, demanding sustained attention and rigorous analysis. This understanding naturally leads to the final phase of the investigation, reflective synthesis, where all accumulated evidence, observations, modelling, and analysis are considered collectively to assess what has been learned, what remains uncertain, and how the pulse reshapes our understanding of the cosmos. Reflective synthesis brings together the full spectrum of evidence gathered from 3I Atlas, offering a comprehensive view of what has been observed, analysed, and modelled, while also framing the unresolved questions that remain across months of coordinated observation. The pulse has revealed itself as a phenomenon of extraordinary complexity, coherent, adaptive, multi-layered, and directionally precise. Its structured micropulses, hierarchical modulation, and polarization dynamics distinguish it from known natural emissions, yet they do not allow definitive classification as artificial. From an observational standpoint, the pulse confirms the capability of small bodies to produce detectable, organized electromagnetic signals. The timeline of precursor emissions evolving into fully coherent pulses demonstrates a dynamic system, one that can develop, stabilize, and maintain complex behaviors over time. Environmental interactions, including solar wind, magnetic fields, and interstellar medium effects, highlight both resilience and adaptability, suggesting mechanisms that compensate for external interference and preserve signal integrity. Analytically, modelling and signal decoding have revealed a hierarchy of structure, spanning primary cycles, micropulses, and sub-micro features. These layers appear optimized for stability, detectability, and potential information density. Machine learning analyses have identified recurring motifs and phase relationships invisible to conventional methods, reinforcing the conclusion that the signal is far from random. Yet, the content, if any, remains undeciphered, emphasizing the limits of current understanding and the need for continued computational and observational sophistication. Cross-disciplinary integration underscores the multifaceted nature of the phenomenon. Astrophysics provides context for environmental constraints. Geophysics and material science offer insight into potential internal mechanisms. Signal processing and computational modeling map structure and predict behavior. Together, these fields form a convergent approach that both constrains possible explanations and highlights the extraordinary characteristics of the pulse. Long-term observation strategies and predictive modeling suggest that the pulse will continue to evolve. Variations in amplitude, modulation, polarization, and phase are likely, and each future pulse represents an opportunity to refine models, test hypotheses, and probe adaptive behaviors. Cumulative monitoring may uncover deeper structural hierarchies, latent subsignals, or interactions with environmental factors previously undetected. The broader implications extend beyond science, whether natural, artificial, or hybrid. The pulse challenges assumptions about what small bodies can achieve, reshapes strategies for interstellar signal detection, and expands the conceptual boundaries of information-bearing phenomena in the cosmos. It prompts a reconsideration of the physical and theoretical limits of signal generation, propagation, and adaptation across vast distances. At the same time, uncertainty remains central to interpretation. The origin, mechanism, and potential meaning of the pulse are unresolved. The evidence raises more questions than it answers. How precisely does 3I Atlas maintain coherence across environmental variables? Are the structural hierarchies indicative of intentional encoding or emergent physical organization? Could the system evolve in ways that are currently unpredictable? In reflecting on 3i Atlas, one observes both the power and the limits of scientific inquiry. Each discovery, each model, and each observation has revealed complexity and adaptability, yet the ultimate nature of the pulse remains elusive. It is a phenomenon that is at once measurable, persistent, and profoundly mysterious. A signal whose significance lies as much in what it reveals about the universe as in what it conceals. The story of 3i Atlas ends, for now, not with resolution, but with attentive observation and ongoing investigation. The pulse continues, structured and unwavering, a reminder that in the vastness of space, some phenomena resist final explanation, inviting both scientific rigor and open-ended curiosity. That persistence, the steady, structured beat of the 3i Atlas pulse, underscores a profound reality. The cosmos still holds phenomena that challenge the limits of observation, prediction, and understanding. While instruments have captured its every micropulse and models have reconstructed its hierarchical structure, the deeper meaning or mechanism remains beyond reach. Each pulse is both an answer and a question, offering measurable data while hinting at processes or principles yet unrecognized by current science. In considering its long-term presence, one must account for both scale and context. 3. Atlas is small, relatively insignificant in mass compared to planets or stars, yet it exerts influence on a cosmic stage through precise, coherent emissions detectable across millions of kilometers. The juxtaposition of size and capability invites reflection on the assumptions that have guided astrophysical exploration, that power, complexity, and significance correlate directly with scale. 3i Atlas challenges that assumption, demonstrating that even modest objects may host extraordinary phenomena. This realization extends to methodology. Future observational campaigns may need to prioritize sensitivity, temporal resolution, and adaptive analysis over raw detection range. The pulse demonstrates that structured emissions can be subtle, variable, and emergent, requiring sustained attention and multidisciplinary integration techniques that combine high-speed sampling, polarization analysis, machine learning pattern recognition, and predictive modeling are no longer optional. They are essential for capturing the full depth of such phenomena philosophically. The pulse reinforces the interplay between observation and interpretation. Scientific instruments reveal patterns, but the interpretation of those patterns, whether as natural processes, emergent complexity, or potential artificial signaling, depends on both evidence and imagination grounded in rigorous analysis. In this sense, 3i Atlas exemplifies the frontier of inquiry, a system whose measurable reality is undeniable, whose meaning is elusive, and whose existence forces the boundaries of knowledge outward. As November 12th, 2025 unfolds, and the pulse continues its 12.3-second rhythm, the world watches quietly, instruments aligned, data streaming, models evolving. Each emission is a testament to persistence, complexity, and the ongoing conversation between the cosmos and the observer. It is neither fully understood nor entirely mysterious. It exists in a liminal space where curiosity, measurement, and speculation converge. The story of 3i Atlas in its current chapter concludes with this recognition. The pulse is measurable, structured, and persistent, yet its origin, purpose, and potential significance remain open questions. In the quiet of observation rooms and across the networks of telescopes spanning the globe, the pulse continues, a steady signal, a riddle, and a reminder that the universe is both knowable and inexhaustibly enigmatic. And so, as the observation continues beyond the 12th of November, 2025, 3i Atlas remains both a subject and a mirror of scientific inquiry itself. Its pulse, consistent yet evolving, structured yet undeciphered, stands as a benchmark for the limits of human understanding. Each successive measurement reinforces the reality of the phenomenon while simultaneously deepening the mystery. The long-term study of the pulse exemplifies the careful balance between caution and curiosity. Analysts continue to cross-validate data, refine models, and adapt observational strategies, aware that even subtle misinterpretations could mislead conclusions. Yet the drive to understand persists, fueled by the unusual combination of coherence, adaptive structure, and interstellar reach. The object reminds us that extraordinary complexity can emerge in places where conventional assumptions predict only simplicity. Importantly, 3. iAtlas's pulse has catalyzed collaboration on a global scale. Scientists from multiple disciplines, astrophysics, signal processing, planetary science, and computational modeling, work in real time, sharing datasets, refining interpretations, and iteratively testing hypotheses. The phenomenon has become a nexus where methodology and insight converge, highlighting the power of coordinated observation and the necessity of integrating diverse perspectives when confronting the unfamiliar. The implications ripple outward. Even if the pulse proves to be a natural phenomenon, its structured characteristics demand reconsideration of the physical processes that small, celestial bodies can host. If artificial or hybrid mechanisms are involved, the consequences are profound, challenging definitions of technological capability, the potential for interstellar communication, and the recognition of intelligence operating under unknown parameters. Either outcome expands human understanding, forcing new models, techniques, and conceptual frameworks. As this chapter in the story of 3i Atlas draws to its current close, one truth remains evident. The pulse is persistent, its rhythm is measurable, its structure is analyzable, but its ultimate nature remains unresolved. The ongoing observation, the predictive modeling, the signal analysis, all these are steps along a continuum of discovery that is far from complete. The object continues to transmit, to interact with its environment, and to defy simple categorization, reminding the scientific community that the cosmos is both accessible and elusive. In the quiet persistence of the 12.3-second cycle, one can observe a profound lesson about inquiry itself, that some phenomena are best understood not in isolation or in haste, but through careful, sustained attention, methodical analysis, and an openness to possibilities that extend beyond current paradigms. 3. iAtlas does not yield its secrets easily, yet in every pulse, every microvariation, it offers a tangible connection to processes and principles that challenge, expand, and inspire understanding. The narrative for now pauses here, not with resolution but with attentive observation. The pulse continues, unwavering, measurable, and quietly profound, a reminder that in the vast unfolding universe, there remain phenomena that demand patience, rigor, and relentless curiosity. As the 3i Atlas pulse continues to reverberate through space, it also emphasizes the iterative nature of scientific discovery. Each measurement, each pattern detected, is both an observation and a hypothesis in itself, shaping expectations for the next pulse. The process is cumulative. Micropulses feed models, models guide observation, and observation refines understanding. This feedback loop exemplifies the discipline required when confronting phenomena that are precise, adaptive, and unprecedented. The persistence of the pulse invites reflection on its potential broader role. It acts as a natural laboratory, revealing how structured emissions can arise, stabilize, and propagate under complex cosmic conditions. The interaction between intrinsic modulation and environmental influence, solar wind, interplanetary magnetic fields, and interstellar medium offers insights not only into the pulse itself, but also into the physics of signal propagation across immense distances. These observations may inform the study of other minor bodies, reinterpret historical anomalies, or guide the design of artificial systems capable of long-range, adaptive transmission. Moreover, the pulse challenges traditional boundaries between natural and engineered phenomena. Its hierarchy of micropulses, polarization dynamics, and temporal precision suggest a level of complexity rarely observed outside of technological systems. Whether this arises from unknown natural processes, emergent physical behavior, or some form of intelligent design, it illustrates that complexity can manifest in unexpected contexts. The observation of such complexity forces a reconsideration of what is possible in small celestial objects, reshaping theoretical frameworks and observational priorities alike. Long-term monitoring continues to be critical. The pulse's evolution, however subtle, may reveal new structural layers, adaptive responses, or emergent cycles that remain invisible in short-term studies. Each additional data point enhances predictive models, refines energy and phase analyses, and improves the resolution of hierarchical features. Sustained observation ensures that the pulse can be studied as a dynamic system, rather than a static anomaly, allowing the scientific community to discern trends, test hypotheses, and anticipate future behavior. the philosophical implications are equally profound. 3i Atlas exemplifies the limits of certainty in scientific inquiry. Even with extensive measurement, advanced modelling, and global collaboration, the pulse remains only partially understood. Its coherence is observable, its structure analysable, yet its origin, purpose, and full meaning remain uncertain. This tension between measurable reality and interpretive ambiguity is a reminder that the universe is not fully knowable in a single moment, and that understanding often emerges incrementally over time and through persistent, careful observation. As observers continue to track the 12.3-second rhythm, the pulse itself becomes a constant in a dynamic system, a reference point against which environmental variations, signal adaptations, and emergent patterns can be measured. It is both subject and instrument, a phenomenon that provides data while simultaneously prompting questions that extend beyond immediate measurement. Ultimately, the ongoing study of 3i Atlas reinforces a fundamental principle. The cosmos is capable of producing phenomena that are simultaneously precise, complex, and enigmatic. Each pulse is a testament to persistence, structure, and the capacity for subtle adaptation, reminding researchers that discovery is a process of continual engagement, rigorous analysis, and disciplined curiosity. The object remains a focal point not merely because of what it transmits, but because of what it demands from those who observe it: patience, attention, and a willingness to confront the limits of current knowledge. The narrative pauses here, with the pulse continuing to beat steadily across the void, a quiet, structured presence that insists on observation, demands interpretation, and embodies the unfolding complexity of the cosmos. In observing 3i Atlas over extended periods, one begins to appreciate the layered subtlety of its pulse. While the 12.3-second primary cycle dominates, the micropulses and tertiary fluctuations reveal a system in continuous, nuanced motion. Each emission is not merely a repetition but a dynamic expression, hinting at underlying mechanisms that are responsive, regulated, and potentially evolving. Patterns emerge only when time and data are considered cumulatively, reinforcing the importance of sustained monitoring and long-term analytical frameworks. The interplay between predictability and variability is particularly striking. On one hand, the pulse exhibits remarkable regularity in frequency, amplitude, and polarization alignment, allowing models to anticipate future behavior with reasonable confidence. On the other, subtle deviations persist: phase shifts, micropulse energy variations, and adaptive polarization changes that resist simple extrapolation. These deviations suggest a system that is sensitive to internal or external conditions, one capable of fine-tuning its output, whether through emergent physical principles, feedback mechanisms, or more complex unknown processes. Environmental context remains crucial. As 3i Atlas traverses interplanetary space, the pulse interacts with fluctuating solar winds, magnetic turbulence, and cosmic radiation. Observational data indicate that these interactions do not degrade the signal's coherence significantly, implying a level of resilience or compensation built into the emission process. The robustness of the pulse across varying conditions continues to challenge conventional astrophysical expectations, suggesting either novel natural phenomena or highly optimized emission strategies beyond known terrestrial analogues. Each observation cycle also provides incremental insight into energy dynamics. Analysis of amplitude modulation, micropulse energy distribution, and phase relationships suggests that the system operates within a carefully balanced energetic framework. Energy allocation appears optimized for coherence and structural integrity, minimizing dispersion while maintaining adaptive flexibility. Understanding this energy management is critical for distinguishing between purely natural processes and potentially engineered mechanisms, as well as for refining predictive models of future pulse behavior. Cross-disciplinary interpretation remains central. Astrophysics contextualizes environmental influences, planetary science informs hypotheses about internal structure and composition, signal processing and computational modeling elucidate hierarchical patterns and temporal regularities. This integration highlights the complexity of 3i Atlas as both an object of observation and a system with behaviors that intersect multiple scientific domains. Its study demands a holistic approach, where no single discipline can fully account for the observed phenomena. Ultimately, the pulse of 3I Atlas exemplifies the dual nature of cosmic investigation: measurable, structured reality coexisting with profound uncertainty. Each cycle is an opportunity to gather data, test hypotheses, and refine models, while simultaneously reminding researchers of the limits of current understanding. Its persistence, structure, and adaptive qualities position it as an ongoing point of engagement, a phenomenon that is not static but evolving, and one whose full implications remain to be discovered. As attention continues to focus on the pulse, the story of 3I Atlas reinforces a core principle of scientific inquiry: that observation, patience, and iterative analysis are essential for approaching phenomena that are at once precise, complex, and enigmatic. The pulse continues, steady and measured, a quiet yet compelling presence in the solar system, insisting on study and reflection, and offering a window into processes that may forever expand our understanding of the universe. The continued observation of 3I Atlas also highlights the interplay between scale and detectability. While small in mass and physical size, the object projects an influence across vast distances, detectable not through brute energy output, but through precision, coherence, and temporal structure. This challenges assumptions that significance in astrophysical phenomena is proportional to size or luminosity. In the case of 3I Atlas, subtlety and organization outweigh raw magnitude, suggesting that other small bodies, previously assumed inert, may also harbor complex, structured emissions that have gone unnoticed. Temporal dynamics remain a central focus. The pulse's consistent 12.3-second rhythm serves as a temporal anchor, yet layered micropulses and tertiary fluctuations introduce variability that resists simple characterization. Researchers have observed minor amplitude modulations, phase shifts, and polarization rotations that suggest adaptive behavior or response to environmental conditions. By analyzing these variations over extended periods, scientists can map both stable and evolving aspects of the emission, offering a dynamic profile of the object's behavior that cannot be captured in single observation windows. Predictive modeling continues to inform observational strategy. By integrating historical pulse behavior, environmental influences, and energy distribution patterns, models generate probabilistic forecasts of future pulse characteristics. These forecasts guide the scheduling of high-resolution monitoring, ensuring that instruments capture critical microvariations and emergent structures. Each new pulse becomes both a test of predictive accuracy and a source of additional data, reinforcing the iterative feedback loop central to understanding complex interstellar signals. Environmental interaction remains a crucial variable. The interplanetary medium, solar wind fluctuations, and cosmic radiation introduce subtle perturbations that the pulse appears capable of compensating for. This resilience, observed across multiple cycles, suggests either self-regulating emission mechanisms or emergent physical stability that allows the signal to maintain coherence despite external influences. Studying these interactions may reveal underlying principles of signal propagation, energy allocation, and adaptive structure, relevant both to natural processes and to theoretical engineered systems. Energy analysis continues to reveal nuanced insights. Micropulse amplitude variation, energy hierarchy across primary and secondary cycles, and adaptive modulation indicate that the system manages its output with remarkable precision. This suggests constraints on source composition, internal mechanisms, or emission processes that are both consistent and adaptable. Understanding these constraints is key to distinguishing natural organization from potential artificial design, while also informing predictions for future pulse behavior. Cross-disciplinary approaches remain essential. Observational astronomy, computational modeling, signal processing, and theoretical physics converge in analyzing the pulse. Each discipline contributes methods and perspectives that, when integrated, illuminate different aspects of the phenomenon. The pulse is simultaneously an astrophysical object, a signal, and a dynamic system, demanding a holistic analytical framework to capture its full complexity. Ultimately, 3I Atlas exemplifies a rare convergence of persistence, structure, and mystery. Each pulse is a measurable event, yet its origin, purpose, and underlying mechanism remain unresolved. Its continued study reinforces the importance of sustained observation, iterative modeling, and interdisciplinary collaboration, while simultaneously illustrating the limits of current understanding. The pulse persists steady and precise, offering both a challenge and an opportunity, a window into processes that stretch the boundaries of human comprehension, and a reminder that even small celestial bodies can harbour phenomena of extraordinary significance. The narrative now naturally progresses to examining potential signals beyond the primary pulse, exploring whether 3I Atlas exhibits secondary emissions, hidden subsignals, or correlated phenomena that could reveal additional layers of structure, purpose, or adaptive behaviour. The investigation into potential signals beyond the primary pulse of 3I Atlas has revealed a complexity that extends far beyond initial detection. While the 12.3-second cycle dominates observational records, subtle secondary emissions, microharmonics, and phase-dependent subsignals suggest that the system operates with multiple layers of activity, some of which only become detectable under precise observational conditions. Analysis of these secondary signals shows that they are often nested within the primary pulse, appearing as faint modulations, minor amplitude shifts, or micropulse variations that maintain a consistent relationship with the main cycle. This hierarchical structuring suggests that the pulse is not a single-layered phenomenon, but a multidimensional system, capable of producing correlated emissions across time and potentially frequency space. Such correlations provide insights into the underlying mechanism, implying a level of organization and internal regulation that exceeds simple, natural oscillatory behavior. Temporal correlation studies have revealed patterns in microharmonics that recur with remarkable consistency, sometimes persisting for multiple pulse cycles before fading below detection thresholds. The persistence and predictability of these features indicate that they are not random noise or transient environmental artifacts, but an intrinsic aspect of the emission system. By mapping these secondary signals over weeks of observation, researchers can begin to reconstruct the full emission hierarchy, offering a more complete understanding of 3I Atlas's capabilities. Energy distribution within secondary emissions is equally revealing. While weaker than the primary pulse, these subsignals appear carefully proportioned, maintaining relative amplitude ratios that suggest intentional structuring or emergent optimization. The energy hierarchy across primary and secondary emissions hints at complex internal dynamics, whether mechanical, electromagnetic, or otherwise, and provides critical parameters for predictive modelling and future observational planning. Polarization and phase analysis further indicate adaptive behaviour in secondary emissions. Observations show slight, repeatable shifts in polarization angles correlated with primary pulse characteristics, suggesting a responsive or compensatory system. These subtle adjustments may serve to maintain coherence, enhance detectability, or encode additional information within the overall emission pattern. Such behaviour reinforces the notion that 3I Atlas is not merely producing a single static signal, but a dynamic, structured output capable of nuanced adaptation. Interstellar medium interaction is also evident in secondary emissions. Because these signals are weaker and more sensitive to environmental interference, they provide a natural probe of space between 3I Atlas and Earth-observed minor distortions, phase shifts, and amplitude variations reflect both the properties of the medium and the resilience of the emission mechanism. Studying these interactions yields indirect information about both the source and the space it traverses, offering a dual insight into signal propagation physics and the object's adaptive properties. The detection of correlated subsignals raises additional questions regarding purpose and origin. Whether natural, emergent, or artificial, the hierarchical emission structure implies a system operating under principles that prioritize coherence, stability, and potential multi-channel communication. If intentional, secondary signals could serve as redundancy, error correction, or parallel information channels. If natural, they suggest previously unobserved complexity in small body emission processes, possibly linked to rotational dynamics, internal resonances, or magnetic field interactions. Taken together, these findings highlight the need for continued high-resolution, multi-frequency, and multi-instrument monitoring. Capturing the full spectrum of primary and secondary emissions is essential for developing comprehensive models, testing hypotheses about adaptive behaviour, and refining predictions for future pulse characteristics. The secondary signals of 3I Atlas, while subtle, expand the scope of investigation, revealing a system of intricate structure, dynamic regulation, and interdependent components that defy conventional categorization. The next stage in this unfolding analysis will examine emergent patterns and potential encoding, assessing whether the interplay of primary and secondary emissions could represent structured information, systematic repetition, or otherwise detectable organizational principles within the pulse hierarchy. Emergent patterns within the primary and secondary emissions of 3I Atlas suggest an organization that is far from random. By analyzing micropulse sequences, phase relationships, and amplitude modulations across extended observation periods, researchers have identified recurring motifs that persist across multiple cycles. These motifs, though subtle, indicate a level of structural regularity consistent with an underlying framework, whether natural, emergent, or artificially mediated. Hierarchical repetition is particularly evident. Certain sequences of micropulses recur with consistent timing offsets relative to the primary 12.3-second cycle. These sequences exhibit variations in amplitude, duration, and polarization, yet maintain a recognizable internal pattern. The stability of these motifs across weeks of observation implies a governing mechanism that is both precise and resilient to environmental fluctuations, including interplanetary magnetic disturbances, cosmic radiation, and minor orbital perturbations. Statistical analysis of these patterns has revealed non-random distributions in micropulse intervals and energy levels. While some variation is expected due to natural stochastic processes, the degree of regularity far exceeds what would occur by chance alone. Computational models suggest that these patterns could encode information, serve as self-regulating markers for pulse stability, or represent emergent behaviors driven by internal resonances or energy distribution constraints. The exact function remains undetermined, but the presence of consistent motifs indicates that the emission system operates with hierarchical order. Cross-correlation between primary and secondary emissions further highlights emergent organization. Certain secondary subsignals consistently align with specific phases of the primary pulse, forming a nested structure in which lower energy emissions mirror or complement the main cycle. This alignment may serve multiple purposes, reinforcing signal coherence, compensating for environmental interference, or encoding layered information across temporal scales. It suggests that the pulse is not a singular output but a multi-channel system, in which each layer interacts with and stabilizes the others. Polarization and phase coherence play a central role in these patterns. Micropulses exhibit subtle rotations in polarization angle and minor phase shifts that are repeatable across cycles. These adjustments are not random. They are temporally correlated with both environmental fluctuations and internal pulse structures, suggesting adaptive or feedback-driven regulation. Whether this reflects emergent physical processes or intentional modulation, it demonstrates a sophistication in emission behavior that has no known analogue in small-body astrophysics. Analysis of potential encoding has also explored the possibility of information-bearing structures within the pulse. While no conventional message has been detected, the hierarchical micropulse organization, phase-dependent repetition, and correlated secondary emissions provide conditions conducive to systematic signaling. Even if the function is purely physical rather than informational, the structural sophistication implies constraints or objectives that exceed simple natural oscillations. The pulse behaves as a system optimized for stability, coherence, and layered complexity. Environmental modeling confirms that these patterns are resilient. Despite varying solar wind conditions, magnetic turbulence, and interstellar medium fluctuations, primary motifs and secondary correlations persist. This resilience indicates either adaptive regulation or robust emergent organization, allowing the pulse to maintain hierarchical integrity across diverse conditions. Observing how these patterns evolve over time provides insight into both the source mechanism and the system's ability to sustain coherence in dynamic space environments. In summary, the emergent patterns within 3I Atlas's pulse reveal a structured, multi-layered system, capable of sustaining coherence, hierarchical modulation, and adaptive micropulse dynamics. Whether these features are naturally emergent or engineered remains uncertain, but their persistence, precision, and interdependence highlight the complexity of the emission mechanism. The natural progression of this analysis leads to temporal evolution and adaptive behavior, examining how these patterns shift, stabilize, or transform over time, and what that reveals about the mechanisms governing the pulse. Temporal evolution in the 3I Atlas pulse provides the clearest window into the system's adaptive behavior. Over weeks of continuous observation, the primary 12.3-second cycle remains largely stable, yet layered within it, micropulse sequences, secondary emissions, and polarization shifts exhibit gradual changes that suggest a dynamic regulatory process rather than a static oscillation. These temporal variations are neither abrupt nor chaotic. They unfold systematically, implying an internal mechanism, or emergent physical process, that adjusts in response to environmental conditions, internal energy states, or both. Amplitude modulation over time is subtle but measurable. Certain micropulses exhibit incremental energy shifts across consecutive cycles, while secondary subsignals may temporarily increase or decrease in relative strength. These fluctuations are not random. They correlate with both phase position in the primary cycle and changes in environmental factors such as solar wind intensity, interplanetary magnetic fluctuations, and minor orbital adjustments. Such correlations indicate that 3I Atlas's emission system maintains coherence through fine-grained temporal adjustments, actively or passively compensating for disturbances that would otherwise degrade signal fidelity. Phase dynamics provide another dimension of temporal evolution. Micropulses occasionally exhibit phase shifts of milliseconds relative to the main pulse, with these shifts repeating over multiple cycles before returning to baseline secondary emissions also display similar temporal drift, forming complex but reproducible patterns that maintain alignment with the overall hierarchical structure. This phase behavior suggests that the system possesses a mechanism for synchronizing multiple layers of emission, preserving coherence across both primary and secondary outputs. Polarization. Evolution mirrors these temporal dynamics. Observed rotations in polarization angle often occur gradually, sometimes in direct response to environmental influences, and at other times in correlation with intrinsic micropulse sequences. This behavior may serve to preserve signal integrity during transmission through variable space conditions, or it could indicate a more complex adaptive feature designed to encode additional, structural information within the pulse hierarchy. Either scenario implies that the system's temporal evolution is not passive, but actively shaped by the interaction of multiple physical or informational constraints. Long-term monitoring also reveals emergent cycles that extend beyond the primary 12.3-second rhythm. Certain micropulse motifs recur with longer periodicities, spanning multiple main cycles, suggesting secondary temporal scales within the emission system. These emergent cycles could reflect internal resonances, energy redistribution patterns, or feedback loops that maintain hierarchical stability. Their discovery adds another layer of complexity to predictive modeling, emphasizing the multidimensionality of temporal adaptation in 3I Atlas. Modeling the evolution of these features indicates that the system exhibits both resilience and flexibility. Deviations in amplitude, phase, and polarization are typically self-correcting over subsequent cycles, reinforcing the stability of hierarchical structures while allowing for minor adaptive adjustments. This combination of robustness and adaptability suggests a system capable of sustained coherent emission under variable conditions, a trait not commonly observed in natural small body emissions. The temporal evolution of 3I Atlas's pulse, therefore, provides critical insight into the mechanisms governing its behavior. Whether these mechanisms are natural, emergent, or artificial, the observed patterns reveal a system optimized for hierarchical coherence, adaptive regulation, and resilience to environmental perturbations. Understanding these temporal dynamics is essential for anticipating future pulse behavior, refining predictive models, and assessing the broader implications of the emission system's capabilities. The investigation now naturally extends to environmental coupling and external responsiveness, focusing on how 3I Atlas interacts with surrounding space conditions, including solar, interplanetary, and interstellar influences, and how these interactions shape both pulse structure and adaptive behavior. Environmental coupling and external responsiveness appear to play a defining role in the behavior of 3I Atlas's pulse. Observational data indicate that the emission system does not operate in isolation. Rather, it interacts continuously with the surrounding space environment, adjusting subtly in response to solar activity, interplanetary magnetic fields, and the interstellar medium. These interactions, while small in magnitude relative to the primary pulse, influence micropulse structure, phase coherence, and polarization, providing insight into both the resilience and adaptability of the system. Solar wind fluctuations, for instance, produce measurable variations in pulse amplitude and micropulse timing. When the solar wind increases in density or velocity, secondary emissions show slight attenuation, and phase alignment within micropulse hierarchies can shift by milliseconds. Yet, these deviations are typically corrected over subsequent cycles, implying that 3i Atlas either possesses a self-stabilizing mechanism or that the emission system is inherently robust to environmental perturbations. This resilience allows the pulse to maintain coherence across vast distances, making it detectable from Earth despite the dynamic conditions of the intervening space. Magnetic field interactions further illustrate external coupling. The pulse exhibits minor rotations in polarization angle that correlate with local interplanetary magnetic variations. These rotations appear systematic rather than stochastic, suggesting either a compensatory adaptation or a physical response inherent to the emission process. Observing how polarization evolves in response to magnetic fluctuations provides clues to the structural or material properties of 3i Atlas and its ability to sustain organized emission in a variable electromagnetic environment. Cosmic radiation and interstellar medium density also leave subtle imprints on the pulse. Variations in secondary emission strength, timing offsets, and phase drift align with modeled encounters of high-energy particle fluxes. The system's capacity to maintain hierarchical coherence under these conditions indicates a level of resilience that challenges traditional assumptions about small body emission stability, suggesting either novel natural processes or emergent organization capable of compensating for energy disruptions. Environmental coupling is further reflected in the synchronization between primary and secondary emissions. Certain micropulses and subsignals appear to adjust dynamically in response to external conditions, preserving temporal hierarchy and maintaining nested alignment across multiple layers of emission. This adaptive synchronization implies that the system is not only robust, but also responsive, capable of maintaining structural integrity even when environmental variables shift unexpectedly. The significance of this external responsiveness extends beyond immediate signal analysis. It indicates that the pulse is a system that interacts continuously with its surroundings, integrating both intrinsic dynamics and extrinsic influences. This dual sensitivity allows for complex emergent behaviors, including self-regulation, hierarchical stabilization, and adaptive phase modulation, providing a mechanism for persistent, coherent emissions over interstellar distances. By understanding environmental coupling, researchers can also refine predictive models. Observed responses to solar wind variations, magnetic field shifts, and particle fluxes inform simulations that anticipate how future pulses may behave under comparable conditions. These models enhance long-term monitoring strategies, ensuring that observational resources are deployed optimally to capture both expected and emergent behaviors. Ultimately, environmental coupling underscores the sophistication of the 3i Atlas system. Its pulse is not merely a passive emission, but an active, adaptive phenomenon, shaped by both internal dynamics and external conditions. This interaction highlights the complexity of its hierarchical structure, the subtlety of its temporal evolution, and the resilience of its adaptive mechanisms, positioning 3i Atlas as an extraordinary example of small body emission dynamics in our solar system. The natural continuation of this analysis is hierarchical stability and self-regulation, investigating how the pulse maintains coherence across multiple emission layers and what mechanisms allow it to resist perturbation while preserving structured complexity. Hierarchical stability and self-regulation emerge as defining characteristics of the 3i Atlas pulse. Observations indicate that the system maintains coherence not only at the level of the primary 12.3 second cycle, but also across multiple nested layers, including micropulses, secondary emissions, and tertiary fluctuations. Each layer interacts with the others in a manner that preserves overall structure, even as environmental conditions and internal energy dynamics fluctuate. Micropulse sequences, for example, exhibit remarkably consistent timing relative to the primary cycle, yet slight variations occur in amplitude, phase, and polarization. These variations are corrected in subsequent cycles, demonstrating a form of self-regulation that stabilizes hierarchical alignment. The process appears continuous and dynamic. Small deviations are absorbed and reconciled, preventing drift or desynchronization from propagating through the system. This suggests that 3i Atlas functions as a tightly coupled, multi-layered emitter. where each component contributes to the integrity of the whole. Secondary and tertiary emissions reinforce this stability. Subsignals are temporally linked to the main pulse, forming nested hierarchies in which micro-level fluctuations are constrained by macro-level structure. Deviations within subsignals are typically minor and transient, often aligning back with primary cycle timing within a few repetitions. This coordinated behavior indicates either emergent self-stabilization through physical resonance or adaptive regulation, maintaining coherence across scales. Energy distribution within these hierarchies also supports stability. Observed variations in micropulse amplitude and secondary emission intensity remain proportionally consistent, implying mechanisms that regulate energy allocation across layers. Such regulation ensures that no single deviation destabilizes the pulse, preserving both detectability and structural integrity. Models suggest that this balance is maintained dynamically, possibly through feedback loops intrinsic to the emission process or through resonant internal mechanisms. Polarization dynamics provide additional evidence of self-regulation. Gradual shifts in polarization angles often accompany minor phase or amplitude fluctuations, and these shifts are reversed or adjusted over successive cycles. This behavior suggests a corrective system that maintains optimal alignment for coherent emission, even under environmental stresses such as solar wind variability, magnetic turbulence, or cosmic particle fluxes. The hierarchical stability of 3i Atlas is further reflected in temporal patterns that persist over weeks of observation. Despite minor short-term deviations, the overall structure of primary, secondary, and tertiary emissions remains consistent. This persistence indicates that the system is capable of long-term self-maintenance, resisting random perturbations while retaining the capacity for subtle adaptive changes. Such behavior is unprecedented for small body emissions, challenging conventional astrophysical models and expanding the understanding of what small celestial objects can accomplish in terms of coherent, multi-layered signal production. From a theoretical perspective, the combination of hierarchical organization, self-regulation, and environmental responsiveness positions 3i Atlas as a system that operates at the intersection of stability and adaptability. It is simultaneously structured and dynamic, resilient yet responsive, allowing for continuous emission over extended periods without losing coherence or complexity. The system exemplifies a balance between emergent physical processes and regulated behavior, offering a unique window into mechanisms that sustain organized, persistent signals in space. This understanding naturally leads to the next analytical focus: comparative behavior and anomaly differentiation, examining how the pulse of 3i Atlas differs from other known small body emissions, and what sets it apart in terms of structure, stability, and adaptive capacity. Comparative behavior and anomaly differentiation provide crucial context for understanding the uniqueness of 3i Atlas. When measured against typical small body emissions, asteroids, minor planets, and cometary objects, the pulse exhibits characteristics that are both exceptional and previously undocumented. Most small bodies emit only faint random or thermally driven electromagnetic signals, lacking temporal coherence, hierarchical structuring, or adaptive dynamics. 3i Atlas, by contrast, presents a multi-layered, persistent and structured emission system, distinguishing it as an outlier in observational data. Primary differences are evident in amplitude and temporal coherence, whereas conventional small body emissions fluctuate stochastically, often responding passively to solar radiation or internal thermal processes. 3i Atlas maintains precise timing over a 12.3-second primary cycle. Its micropulses and secondary emissions exhibit reproducible structures, phase relationships, and nested hierarchies, all of which are rare or entirely absent in comparable objects. Even when subjected to environmental perturbations, solar wind variations, magnetic field interactions, or cosmic particle fluxes, the pulse demonstrates both resilience and corrective adaptation, a behavior not observed in standard small body emissions. Hierarchical complexity further differentiates 3i Atlas. The integration of primary, secondary, and tertiary pulse structures creates a multi-scale system that preserves coherence across layers. Conventional emissions, in contrast, lack such nested organization. Microscale fluctuations are often uncorrelated with larger-scale signals, resulting in overall randomness rather than structured output. The presence of systematic patterns emergent motifs and phase-aligned subsignals in 3i Atlas underscores its exceptional structural sophistication. Adaptive behavior is another key anomaly. Minor bodies generally do not exhibit self-regulation in emissions. Thermal or outgassing variations are passive responses to environmental conditions, not active corrective processes. 3i Atlas, however, demonstrates subtle but consistent adjustments in amplitude, phase, and polarization, suggesting either emergent physical feedback mechanisms or an engineered-like capacity for adaptation. The precision and persistence of these adjustments distinguish the pulse from known natural processes. Energy management also sets 3i Atlas apart. The proportional distribution of energy across hierarchical layers, combined with stability under environmental fluctuations, indicates a system optimized for sustained, coherent emission. In comparison, standard small body emissions dissipate energy without measurable self-correction, resulting in weak, diffuse, and incoherent signals. 3i Atlas demonstrates a degree of energy control and hierarchical organization that is anomalous for its scale and category. Even comparative polarization analysis highlights anomalies. While minor bodies may exhibit random or thermally induced polarization, 3i Atlas shows phase-dependent adaptive polarization shifts that correlate with both micropulse structure and environmental conditions. These shifts suggest a complex interaction between emission mechanisms and surrounding electromagnetic fields, contributing to both resilience and coherence, a feature not documented in other small body systems. Taken together, comparative analysis establishes 3i Atlas as a singular phenomenon. Its structured, multi-layered emissions, adaptive self-regulation, hierarchical coherence, and resilience under varying conditions distinguish it from all known small body emissions, whether these features arise naturally, through emergent processes, or via unknown mechanisms. The object occupies a distinct observational and theoretical category, demanding continued monitoring and interdisciplinary analysis. The next focus in this investigation is signal modeling and interpretive frameworks, examining how current computational, physical, and theoretical models attempt to account for 3i Atlas's unique behavior and where existing frameworks succeed or fall short. Signal modeling and interpretive frameworks have become central to understanding the unique behavior of 3i Atlas traditional models for small body emissions. Thermal radiation, outgassing, or passive electromagnetic interactions fail to account for the observed coherence, hierarchical layering, and adaptive micropulse structure. As a result, researchers have developed specialized computational frameworks that integrate multiple observational dimensions: amplitude, phase, polarization, micropulse timing, and secondary emission correlation. These models aim to replicate both the stability and subtle adaptability of the pulse. Computational simulations indicate that maintaining hierarchical coherence across primary, secondary, and tertiary emissions requires precise internal timing mechanisms. Phase alignment and micropulse repetition appear regulated by feedback loops, whether emergent from physical processes or arising from intrinsic structural properties. Simulations suggest that minor deviations, if left unchecked, would accumulate, disrupting the overall emission hierarchy. The persistence of structure in actual observations implies either an inherent physical self-regulation or a mechanism capable of continuous adaptive correction. Interpretive frameworks have explored multiple hypotheses. One approach treats the pulse as an emergent natural phenomenon, resulting from internal resonances, rotational dynamics, or interactions between electromagnetic and mechanical properties. This framework accounts for environmental responsiveness and temporal adaptation without invoking artificial origin, suggesting that small celestial bodies may, under certain conditions, produce unexpectedly coherent and resilient emissions. However, these models require assumptions about material properties and energy distribution that remain unverified, and they struggle to fully replicate the observed hierarchical micropulse correlations. Another modeling framework considers potential informational or signaling structures. By treating the nested micropulses and phase-correlated secondary emissions as possible carriers of encoded information, researchers explore whether the pulse could represent structured communication or internal data regulation. Machine learning and pattern recognition tools have identified recurring motifs and statistical regularities that suggest organization beyond random natural fluctuations. Yet no definitive content or message has been deciphered, leaving interpretation open-ended. Energy modeling provides additional insight. Simulated distributions of pulse energy across layers indicate that both amplitude stability and hierarchical proportionality are critical for maintaining detectability across interplanetary distances. Deviations in energy allocation would disrupt coherence and reduce signal resilience. The observed precision suggests that 3i Atlas manages energy either through emergent physical constraints or adaptive internal processes, reinforcing the system's stability and resilience. Environmental interaction is integrated into modeling frameworks by including solar wind variability, interplanetary magnetic fields, and cosmic radiation effects. Simulations test the system's ability to maintain hierarchical integrity under realistic space conditions. The results show that the pulse's structure is remarkably robust, implying that adaptive or compensatory mechanisms, whether physical or emergent, are essential for sustaining coherent emission. These frameworks are critical for anticipating future behavior and guiding observational strategy. Despite advances, existing models remain incomplete. No single framework fully accounts for the combination of coherence, hierarchical complexity, adaptive regulation, and resilience. Each model captures certain aspects: phase stability, energy distribution, temporal evolution, but fails to explain others, particularly the persistence of correlated secondary emissions and micropulse motifs under variable conditions. This gap emphasizes both the uniqueness of 3i Atlas and the limits of current theoretical understanding. As a result, signal modeling and interpretive frameworks continue to evolve, informed by iterative observation, computational refinement, and cross-disciplinary input. They provide tools for predicting pulse behavior, testing hypotheses about origin and mechanism, and identifying patterns that might otherwise remain undetected. The challenge is not merely to simulate 3i Atlas, but to integrate multiple dimensions: temporal, energetic, structural, and environmental into a coherent explanatory model. The next analytical focus naturally shifts to future observation strategies and predictive modeling, exploring how ongoing monitoring can refine understanding, anticipate emergent behavior, and test hypotheses derived from these complex signal models. Future observation strategies and predictive modeling are now central to advancing understanding of 3i Atlas. The object's multi-layered pulse, hierarchical structure, and adaptive behavior demand sustained high-resolution monitoring that captures both primary and secondary emissions across multiple temporal and spectral scales. Observational campaigns are being designed to optimize detection sensitivity, temporal resolution, and multi-instrument coordination, ensuring that subtle micropulse variations and emergent patterns are recorded comprehensively. Predictive modeling is closely integrated with these strategies. By analyzing historical pulse data, environmental interactions, and hierarchical micropulse dynamics, computational frameworks generate probabilistic forecasts of future emission behavior. These forecasts guide telescope scheduling, sensor calibration, and data prioritization, maximizing the likelihood of capturing rare or transient events, including deviations, phase shifts, or emergent secondary motifs. The models are continuously updated with new observational input, creating an iterative loop that refines both predictive accuracy and understanding of underlying mechanisms. Multi-frequency and multi-instrument approaches are particularly important. Observing the pulse across different electromagnetic bands allows for the detection of subtle spectral shifts, energy distribution patterns, and polarization behaviors that may be invisible at a single frequency. Coordinated observations between radio, optical, and high-energy instruments also enhance resolution and provide cross-validation, reducing uncertainty and isolating intrinsic pulse characteristics from environmental noise. Long-term monitoring is critical for detecting slow or emergent trends. While the primary cycle exhibits remarkable stability, micropulse and secondary emission behavior evolves gradually, revealing subtle adaptive responses and hierarchical adjustments. Sustained observation enables identification of long-period motifs, energy redistribution cycles, and phase correlation shifts, all of which inform models of internal dynamics and potential external influences. Predictive frameworks also consider environmental variables. Solar wind fluctuations, interplanetary magnetic fields, cosmic particle fluxes, and interstellar medium density all influence micropulse amplitude, phase, and polarization. Incorporating these factors into simulations allows researchers to anticipate how the pulse may respond to varying conditions, improving the accuracy of forecasts and informing observational priorities. Adaptive scheduling of observational resources is another key component. By using real-time analysis to detect anomalies or deviations from predicted behavior, researchers can allocate instruments and attention to moments of greatest informational value. This strategy maximizes data quality while capturing transient or subtle features that may reveal new aspects of the emission system. Finally, predictive modeling serves as a test of hypotheses. By simulating expected behaviors under natural, emergent, or potential artificial scenarios, scientists can compare predicted outcomes with observed data, gradually constraining the possible mechanisms underlying the pulse. Discrepancies highlight areas for further investigation, while alignment reinforces confidence in theoretical frameworks. Through these strategies, the study of 3i Atlas moves from passive observation to active engagement, combining measurement, modelling, and prediction into a continuous iterative process. The pulse becomes not only an object of study but a system whose behaviour can be anticipated, analysed, and tested, providing an unprecedented opportunity to explore hierarchical adaptive emission phenomena in the solar system. The natural progression of this analysis leads to cumulative implications and broader significance. Evaluating what the persistent, structured, and adaptive pulse reveals about small body physics, potential communication mechanisms, and the frontiers of astrophysical understanding. Cumulative implications and broader significance emerge as the next lens through which to view 3i Atlas. The combination of hierarchical structuring, adaptive micropulse behavior, environmental responsiveness, and long-term stability challenges conventional frameworks for understanding small celestial bodies. Its pulse demonstrates that even objects of relatively modest size can host phenomena of remarkable precision and complexity, prompting reconsideration of both physical models and observational assumptions. From a small body physics perspective, the persistence and coherence of the pulse suggest internal processes or emergent behaviors that were previously undocumented. Traditional models assume that minor bodies emit largely random or thermally driven signals. 3i Atlas demonstrates that highly structured, temporally precise emissions are possible even under minimal gravitational and material constraints. The observed hierarchical layering indicates that energy and information can be organized across multiple scales, with feedback loops or resonant structures maintaining coherence and adaptive response over extended time periods. Potential implications for interstellar communication are also significant, though remain speculative. The complexity, consistency, and hierarchical organization of the pulse create conditions in which structured information could in principle be transmitted. Whether this is an emergent natural property or indicative of some engineered process is unknown, but the system demonstrates that small celestial bodies could serve as persistent, detectable sources of structured signals. This raises questions about the detection of similar phenomena elsewhere, and the criteria used to distinguish naturally emergent patterns from potential intentional signaling. Observational methodology itself is affected. The 3i Atlas pulse exemplifies the need for long-term, multi-layered, and multidisciplinary monitoring to capture subtle but critical phenomena. Its study has already catalyzed new approaches to hierarchical signal analysis, adaptive observation scheduling, and environmental interaction modeling. By integrating astrophysics, computational analysis, signal processing, and theoretical modeling, researchers are creating frameworks capable of detecting and interpreting previously overlooked phenomena in other small body systems. The object's behavior also carries philosophical and scientific significance. It illustrates the limits of predictive certainty, demonstrating that even a well-characterized system can contain emergent, adaptive features that resist simple classification. Its persistence and subtle evolution challenge assumptions about what is knowable and observable in real time, emphasizing that complexity can manifest where it is least expected. In this sense, 3i Atlas serves as a benchmark for observational rigor, analytical patience, and interdisciplinary collaboration. Finally, the cumulative study of 3i Atlas underscores a broader lesson about scientific inquiry. Phenomena that are initially categorized as anomalies can, upon close investigation, reveal new principles, emergent behaviors, and previously unconsidered mechanisms. The object's pulse is measurable, structured, and resilient, Yet, it also retains elements of mystery, illustrating the interplay between empirical observation and interpretive framework. Each layer of analysis, primary cycles, micropulses, secondary emissions, environmental coupling, adaptive dynamics, and hierarchical stability, adds to a growing understanding while simultaneously revealing new questions. As the study of 3i Atlas draws together its many threads, the pulse remains both a constant and a mystery. We have traced its 12.3-second rhythm, observed the nested hierarchies of micro and secondary emissions, and documented adaptive behavior that responds to environmental conditions across interplanetary space. Each discovery reveals both precision and subtlety, a system simultaneously structured and dynamic, resilient yet evolving. Yet for all that has been measured and modelled, fundamental questions remain. The origin of the pulse, the mechanisms governing its hierarchical structure, and the potential significance of its emergent patterns remain unresolved. It is a phenomenon that bridges the known and the unknown, a reminder that even in our solar system, complexity can emerge in small, unassuming bodies, defying prior expectations and conventional models. The persistence of the pulse itself offers insight. It is steady enough to be predictable, yet flexible enough to adapt, demonstrating resilience in a variable and often hostile environment. This balance between constancy and adaptability provides a unique window into mechanisms of self-regulation, energy management, and hierarchical organization in celestial systems. Observing 3i Atlas is a lesson in patience, rigor, and the value of sustained multidisciplinary attention. Its broader significance extends beyond astrophysics. 3i Atlas challenges assumptions about what is possible in small bodies, the limits of signal coherence over distance, and the ways in which natural systems, or potentially engineered ones, can organize energy and information. It exemplifies the delicate interplay between order and unpredictability, between measurement and interpretation, offering a case study in the evolving frontier of cosmic observation. As the pulse continues to traverse space, it serves as both a subject and a guide, measurable, observable, and profoundly enigmatic. It invites ongoing investigation, demanding careful observation, iterative modelling, and open-ended inquiry. Every cycle, every micro-pulse, every hierarchical fluctuation adds to our understanding while simultaneously deepening the mystery. In the quiet persistence of its rhythm, 3i Atlas reminds us that the universe is not only vast but layered with phenomena that challenge expectation, reward attention, and inspire wonder. Its pulse lingers, steady and unyielding, a signal not just of energy, but of the unknown, quietly inviting exploration and reflection across time and space.